Hello and welcome to the Deep Field channel. I am genuinely delighted to have you here with me. If you enjoy these gentle journeys through the cosmos, please leave a like, subscribe if you haven't already, and let me know in the comments which corner of the globe you are tuning in from tonight. It can just be a simple hello, the name of your city, or a single word. This small gesture tells the algorithm that our space is welcoming, helping us bring more tired minds here to relax. To those of you who have been part of our community for a while, I offer my deepest, most heartfelt thanks. Now, wherever you are, find a deeply comfortable position, let your shoulders drop, and let us begin. What exactly is quantum physics, and why does it so often feel as though the universe is simply making it up as it goes along? The world we are accustomed to, the one we can see and touch, feels solid and predictable. Drop a teacup and it falls, toss a coin and it lands. Close your eyes and the moon remains exactly where it was. Yet in the early 20th century, scientists began to look closer, much closer, and the deeper they peered into the machinery of matter, the stranger things became. Light, they discovered, could act as both a wave and a particle. Particles could exist in multiple places at once until they were measured. And the very act of observing something didn't just reveal what was already there, it seemed to transform it. This wasn't a quirk of faulty data or imprecise equipment, it was real, reproducible, and it challenged the neat, organized laws of classical physics that had reigned for centuries. Quantum physics wasn't just a new branch of science, it was an entirely new way of perceiving reality, a shimmering, bizarre reality where certainty gives way to probability and cause doesn't always precede effect in the way we expect. In this audio, we will gently drift through this world. There is no need to memorize every equation or name. We will move slowly, softly, exploring one mystery at a time, from the early puzzles that knocked scientists off their classical pedestals to the modern questions that still keep physicists awake. So, get cozy, close your eyes if you wish, and let us begin exploring a realm where even the void isn't truly empty, and where everything you thought you knew about reality is only probably true. At the turn of the 20th century, physics felt nearly finished. The laws of motion were understood, thermodynamics was neatly organized, and light was comfortably tucked into the framework of electromagnetic theory. It was a golden age of certainty. Some scientists even believed that all the grand questions had already been answered, leaving only a few strange details to be swept up like dust in the corners of a well-cleaned room. One of those dusty corners involved a very simple question. What happens when you heat an object? When you warm a piece of metal or coal, it glows red, then orange, then white, depending on the temperature. This glow, known as blackbody radiation, comes from how objects emit electromagnetic radiation when heated. It was easy to observe and seemed like it should be easy to explain. Yet, the mathematics refused to cooperate. Classical physics, using the well-known equations of the time, predicted something bizarre. According to the formulas, as a black body's temperature rose, it should emit more and more energy at shorter and shorter wavelengths, particularly in the ultraviolet range. The problem was that this prediction led to infinite energy at high frequencies, a scenario so impossible and absurd that it was dubbed the ultraviolet catastrophe. No tweaking of classical equations could stop the math from collapsing. Reality simply refused to match the predictions. Something was missing. Enter Max Planck in 1899. Planck was a German theoretical physicist with a reputation for careful, methodical thinking. He wasn't particularly radical or rebellious. In fact, he firmly believed in the classical worldview, but he was also a pragmatist. When faced with the black body radiation problem, he did something quietly revolutionary. To fix the math, Planck introduced a small, strange idea. What if energy couldn't be emitted in just any amount? What if instead it came in tiny, indivisible packets, like coins you cannot break in half. These packets would represent the smallest possible units of energy. He called these packets quanta. This was a drastic shift from the continuous view of energy in classical physics. Instead of a smooth flow, energy would arrive in steps, tiny jumps that depended on the frequency of the radiation. Planck even introduced a constant now known as Planck's constant to describe the size of these energy packets. It was unimaginably small, yet mathematically elegant. When he plugged this idea into his equations, something incredible happened. The infinite energy problem vanished. The equations worked. They matched the real world. Planck had solved the ultraviolet catastrophe, yet he didn't entirely believe it himself. In fact, Planck described his solution as a mathematical trick, a clever way to make the numbers behave, but not a true description of how the universe actually worked. He assumed future physicists would find a better explanation that wouldn't require such strange assumptions. Quantization to him was a temporary patch, not a fundamental truth. What he couldn't know at the time was that his trick would become the cornerstone of an entirely new way of thinking. His idea that energy comes in discrete packets laid the groundwork for quantum theory, a theory that would soon unravel much of what classical physics had taken for granted. It is easy to look back and see this as the moment everything changed, but at the time it seemed more like a strange footnote than a revolution. Planck didn't set out to challenge the foundations of physics. He just wanted the math to work. Yet by introducing quantization, he struck the first match in what would become a slow-burning fire, one that would eventually reshape our understanding of light, matter, and the very nature of reality. This humble beginning, hidden in a quiet paper published in 1900, didn't shout its importance. There were no dramatic declarations, no grand pronouncements, just a tiny constant, a new way to think about energy, and a curious little fix for a problem that refused to go away. From that point on, physics would never look complete again. In the early 1900s, light was thought to be thoroughly understood. Thanks to James Clerk Maxwell's equations, scientists had shown that light behaved as a wave, an elegant ripple in the electromagnetic field. It bent, reflected, diffracted, and interfered just as any wave should. And following Planck's quiet introduction of energy quanta, most physicists assumed things would settle into a slightly adjusted new normal. But then came a puzzle involving metal, light, and a surprising refusal to cooperate. It was called the photoelectric effect, and it worked like this. If you shine light on a metal surface, electrons can be ejected from the metal. The idea made sense. Light delivers energy. Energy expels electrons. Nothing extraordinary. According to wave theory, increasing the brightness of the light should increase the energy transferred to the electrons. A brighter wave should knock the electrons loose more effectively. That was the expectation, but that isn't what happened in experiments. Scientists discovered something odd. Shining brighter light didn't necessarily eject electrons with more energy. What mattered most was the frequency of the light. If the light was below a certain frequency, even a blindingly bright light did absolutely nothing. No electrons were ejected. But above that frequency, even a dim beam could strip electrons away with ease. The threshold was sharp, and it made no sense under classical wave theory. This minor inconsistency blossomed into a full-blown mystery. Enter Albert Einstein. In 1905, a year often called his miracle year, Einstein published a paper that changed everything to explain the photoelectric effect. He proposed something bold. What if light wasn't just a wave? What if under certain circumstances it behaved like a particle, a tiny packet of energy traveling in a straight line? Einstein suggested that light was made of individual energy packets, which he called light quanta, later known as photons. Each photon carried a specific amount of energy determined by its frequency. If a photon had enough energy, It could knock an electron off a metal surface. If it didn't, no amount of photons, no matter how many or how bright, could do the job. It was like trying to open a locked door with a handful of keys, none of which fit. It didn't matter how many you had, you weren't getting in. Einstein's idea built directly on Planck's earlier work but went further. He wasn't just using energy packets as a mathematical trick, he was suggesting that light itself was made of these packets, not as a convenient fiction, but as a literal description of how light behaves. It was a revolutionary claim, and not everyone liked it. Many physicists clung tightly to the wave model of light. After all, light clearly exhibited wave behavior. It diffracted around corners and created interference patterns. If light was truly made of particles, how could it also behave like a wave? Einstein didn't deny the wave nature of light. Instead, he proposed something stranger. Light, he said, was both a wave and a particle. It could act as one or the other depending on how you observed it. This duality wasn't just a weird trick of perception, it was fundamental to the nature of light itself. Imagine a sunbeam filtering through a window. It spreads and ripples like a wave, bouncing off dust and glass. But if you were to zoom in incredibly close, you would find tiny quanta of energy, each with its own frequency, colliding with atoms, changing the world one collision at a time. This wave-particle duality is one of the strangest concepts in all of physics, not because it is complicated, but because it defies the very categories we use to describe reality. In the classical world, things are either particles or waves, not both, not neither, and certainly not whatever they feel like being depending on the situation. But the quantum world doesn't ask for permission to make sense. Einstein's photon explanation for the photoelectric effect not only matched experimental results, it did so beautifully. The energy of each photon depended on its frequency, exactly as Planck had suggested, and it neatly explained why low-frequency light, no matter how intense, couldn't eject electrons. The individual photons simply didn't have enough punch. The impact of this idea was immense. In 1921, Einstein was awarded the Nobel Prize in Physics, not for relativity as many assume, but for his explanation of the photoelectric effect. That is how significant this discovery was. Still, even Einstein found the quantum world uncomfortable. He famously resisted the more probabilistic interpretations that would follow in later years. God does not play dice with the universe, he once declared. But dice or not, the rules were changing, and at the heart of those changes was a strange truth. Light, the very thing that illuminates our world, refused to fit into any neat box. It came in quanta, danced like a wave, collided like a particle, and flickered between states, revealing just enough to keep us curious and just enough to keep us uncertain. What began as a simple experiment with light and metal ended up shaking the foundations of physics. Because if light could behave this way, both continuous and discrete, both spread out and pinpoint, what else might be lurking in the quiet corners of the universe, waiting to break the rules? Picture this. You set up a table, place a flashlight at one end, and cut two tiny slits in a piece of cardboard. You shine the light through the slits and look at the pattern it forms on a screen behind them. Not exactly thrilling, right? And yet, in this humble arrangement, two holes and a bit of light, we find one of the most mind-bending experiments in all of science. The double-slit experiment has become something of a legend in physics. Not because it is complicated, in fact, it is almost embarrassingly simple, but what it reveals is anything but. Some physicists have even joked that this is the most dramatic scientific experiment of all time, starring a flashlight and two holes in a piece of cardboard. Let's start with what we would expect. In the world of classical physics, waves and particles behave in very different ways. A wave, like water or sound, spreads out and interferes with itself. Imagine ocean waves passing through two gaps in a barrier. The waves emerge on the other side and overlap, creating a pattern of peaks and troughs that can reinforce or cancel each other out. This is interference. It is well understood and predictable. Now imagine particles like tiny rubber balls fired at a wall with two openings. Some pass through the left slit, others through the right. They don't overlap or interfere. On the screen behind the slits, you would expect to see two clusters of impact points exactly where the slits are. This is particle behavior, simple, no surprises. So what happens when you do this with light? When scientists first shone light through the two slits, they expected it to behave like a wave, and it did. The light spread out and formed an interference pattern, a series of light and dark bands on the screen caused by the peaks of the waves overlapping and canceling out at specific locations. So far, so good. Light, just as Maxwell had predicted, was behaving like a wave. But then things got weird. Using highly sensitive equipment, researchers turned down the intensity of the light source until it fired only one photon at a time. Instead of a steady stream, there were individual particles of light heading toward the slits one by one. Now you would expect these solitary photons to act like particles, each passing through one slit or the other. And if you wait long enough and collect enough impacts on the screen, there should be two bright spots where the particles landed, just like those rubber balls. But that isn't what happened. Even when sent one at a time, the photons gradually built up the exact same interference pattern as before, a pattern that required waves to interfere with themselves. But how could a single photon interfere with itself? Did it pass through both slits at the same time? Was it somehow a wave and a particle simultaneously? This wasn't an illusion. The interference pattern persisted, suggesting that each photon had traveled through both slits simultaneously, like a ghost of itself, exploring all possible paths until it landed. If that wasn't enough to raise some eyebrows, things got even stranger. The physicists decided to peek behind the curtain. They placed detectors at the slits to observe which path the photon actually took. Surely, they thought, we can just watch and settle this once and for all. Did the photon go through the left slit, the right slit, or somehow both? But when they looked, the interference pattern vanished. The moment the detectors were turned on and the photons were observed, the photons stopped behaving like waves. They acted like ordinary particles again, landing behind only one slit or the other, with no more interference, no more ghostly wave behavior. It was as if the very act of observing forced the photon to make a decision, to go left or right, with no superpositions, no blurriness. Reality had been caught in the act and immediately straightened up and acted normal. Turn the detectors off and the interference returned. Turn them back on and it disappeared. The implications were staggering. It wasn't that our measuring devices were disturbing the photons. They were passive, non-intrusive setups. The issue wasn't how we observed, but that we observed at all. It seemed that the mere knowledge of the photon's path, the potential to know, was enough to collapse its wave behavior into a particle state. Reality, in a sense, cared whether it was being watched. This wasn't just a fluke or an experimental error. The double-slit experiment has been repeated countless times with photons, electrons, and even molecules made of hundreds of atoms. The result is always the same. Left unobserved, these particles act like waves and interfere with themselves. Observed, they behave like classical particles and line up neatly. And if that sounds unsettling, well, you aren't alone. This experiment is at the very heart of quantum physics and defies all efforts to explain it in familiar terms. It suggests that at the smallest scales, particles don't follow strict paths. Instead, they exist as a scatter of possibilities, a shimmering cloud of potential outcomes. Only when a measurement is made does that cloud collapse into something definite. Some have tried to imagine the photon as a wave that splits and reunites. Others prefer the language of probability, describing the wave function as a tool to predict outcomes. And still others, in the realm of many worlds, imagine every possibility branching off into its own separate universe. But whatever the interpretation, the facts remain the same. Until we observe, the particle doesn't seem to commit to any state. What began as a simple test with light transformed into a profound mystery about the nature of reality itself. Observation is an active part of shaping the universe. Information holds power over existence. Reality is fundamentally uncertain until we ask it to reveal itself. These aren't just philosophical musings, they are scientific questions rooted in experiments measured and confirmed. The double-slit experiment doesn't give us clear answers, but it gives us a powerful glimpse. The universe, in its essence, is not a clockwork machine. It is a strange, shimmering tapestry woven from possibilities, and it responds in curious ways to our gaze. With two slits, a light source, and a screen, we discovered that the universe winks at us when we aren't looking and stands perfectly still when we are. In the realm of quantum physics, if there is one piece of mathematics whispered throughout the theory, like a secret spell, it is the Schrödinger equation. Now, don't worry, this won't be a math lecture. No one is going to wake up dreaming of partial differential equations, but this particular equation is different. It isn't just a string of symbols scribbled on a chalkboard, it is the silent heartbeat of the quantum world. In the 1920s, physicists were struggling to describe particles that didn't seem to act like particles. Electrons exhibited wave patterns, photons acted like probabilistic ghosts, and the old laws of motion, the ones Newton gave us, simply weren't cutting it anymore. The universe needed a new kind of language. Enter Erwin Schrödinger in 1926. He proposed an equation that described not just how particles moved, but how their wave functions evolved over time. It was elegant, compact, and shockingly effective. And while it might look like a tangle of Greek letters and operators, at its core it tells a simple story. It describes how a quantum system changes. But let's step away from the symbols and get to what really matters. The key concept here is the wave function, often denoted by the Greek letter psi. If that sounds abstract, think of it this way. The wave function is a sort of mathematical whisper that tells us everything we can possibly know about a quantum system, where a particle might be, the probability of it being there, how it is moving or might be moving. The wave function doesn't give us concrete answers, it gives us probabilities. If you imagine a particle as a tiny dot moving through space, classical physics would draw a sharp arrow showing its exact position and velocity. Schrödinger's world doesn't do that. Instead, it gives us a blurry, undulating cloud, a wave that says the particle is probably over here, but it could also be over there, and maybe a little bit higher up. This is where the magic happens. The Schrödinger equation allows us to evolve this cloud over time. It shows how the wave function changes as the particle moves, though it is more about how the possibilities of its position shift and flow. And when we measure the particle, when we ask, "Where are you?" that wave function collapses. Suddenly the cloud vanishes and we get a single definite answer, right here, but only after we look. This wave-based view of reality is profoundly different from the mechanical picture of the universe that came before. Instead of particles tracing predictable paths like planets around the sun, we now see swirling fields of probability, full of uncertainty and ambiguity, until observation pins them down. Let's bring this to something more visual. Imagine you are blindfolded in a room. Somewhere in that room is a silent cat. You can't hear it, you can't see it, but you can throw small balls and listen to the sound they make when they bounce. Over time, you start to build a picture of where the cat might be. Areas with a higher chance, others with less. That mental map you are building is like the wave function. It isn't a picture of reality as it is, but as it could be. Now imagine you could write an equation that told you how your map changes over time. Maybe the cat likes to move to the corners or sit near warm objects. That equation would be your guide to where the cat is likely to be next. That is what Schrödinger did, except instead of cats, he was thinking about electrons. The actual equation is continuous and smooth. It allows these waves of probability to ripple and shift, much like water in a pond. It respects the underlying symmetries of nature, like the conservation of energy and the flow of time, but it doesn't care much for certainty. It tells us what could happen, not what will happen. And what is fascinating is how beautifully it works. Physicists have used the Schrödinger equation to describe everything from the structure of atoms to how molecules bond, from the behavior of semiconductors to superconductors. It even predicts exotic phenomena like quantum tunneling, where particles pass through barriers they shouldn't be able to cross. The equation itself is timeless, gliding smoothly forward with every moment, offering a map of the unknowable. One of its most famous successes was in explaining the hydrogen atom, the simplest atom in the universe. Before quantum mechanics, no one could fully explain why electrons around a nucleus seem to settle into specific orbits rather than spiraling inward or flying away. The Schrödinger equation revealed that electrons aren't buzzing around like miniature planets. Instead, they form standing waves, stable patterns of probability around the nucleus. These are the orbitals you might have seen drawn as soft clouds or shapes in textbooks. And these clouds aren't just visual metaphors. They represent the actual, measurable probability of where an electron might be found if you decide to look. They aren't orbits, they are zones of presence, and they exist only because the electron isn't a simple particle, but a ripple in a sea of probabilities. It is strange, certainly, but also beautifully consistent. Unlike some theories that need patches or caveats, the Schrödinger equation has aged like fine wine. It works. It has repeatedly predicted the behavior of the very small with astonishing precision, and yet it remains hauntingly abstract. You cannot hold a wave function, you cannot see it, but it is there, describing the ghostly potential of everything from an atom in your tea to the electronics in your phone. And then there is the philosophical side. What exactly is a wave function? Is it a description of our knowledge, or is it a real part of reality, something that truly exists until it collapses into a result? Different interpretations of quantum mechanics argue fiercely about this, but the equation itself takes no sides. It simply does what it does quietly, reliably, and strangely. Even Schrödinger himself had mixed feelings. Although he was proud of the equation, he disliked the idea that particles had no defined properties until they were observed. His famous thought experiment involving a cat that is both alive and dead at the same time was conceived as a critique of the very uncertainty his work had unleashed. He gave us the mathematics of quantum waves and then questioned what those waves actually meant. Still, it is hard not to admire what he built. In a world that often demands yes or no here or there, Schrödinger offered something gentler, a shimmering, maybe a softly pulsing guide to what could be. His equation doesn't shout or command, it suggests, it flows. And in doing so, it reveals a version of the universe that is quieter, subtler, and far more mysterious than we ever imagined. At the most minute scales, motion isn't always motion. Position isn't always position, and certainty is more of a luxury than a rule. But thanks to one elegant equation, we can still find our way softly mathematically through the mist. In the classical world, the world of apples, bicycles, and bowling balls, you can know where something is and how fast it is going at the same time. It isn't even a question. A radar measures a car's speed, while GPS tells you exactly where it is. No mystery, no contradiction. But the quantum world doesn't play by those rules. In the 1920s, Werner Heisenberg introduced a principle so strange and so central to quantum mechanics that it still makes students and scientists pause. It is called the uncertainty principle, and it tells us that at the most fundamental level of reality, there are limits to what we can know. Specifically, it states, the more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa. Now momentum is just mass times velocity. It is a measure of how much motion something has. And if you think about it in everyday terms, this principle sounds almost silly. How can knowing where something is make you unsure of how fast it is going? If you see a train pulling into the station, you know both its position and its speed. Easy. But at the quantum scale, reality doesn't allow that kind of clarity. This isn't about our measuring instruments being clumsy or crude. It isn't a matter of needing better technology. The uncertainty isn't in our instruments. It is woven into the very fabric of the universe. Let's say you are trying to observe an electron. You want to know where it is and how fast it is moving. To do this, you might shine some light on it, but light is made of photons, and photons carry energy. When one of those photons hits the electron, it changes the electron's motion. It is a bit like trying to find a soap bubble in the dark by throwing tennis balls at it. You will certainly find it, but you will also destroy it in the process. Still, Heisenberg's point wasn't just about disturbing particles. His principle is embedded in the mathematics of quantum mechanics. Even if you could observe without interfering, watching through some ghostly, non-intrusive means, the uncertainty would still be there. It isn't a flaw, it is a feature. At the heart of the uncertainty principle is the wave nature of particles. Imagine trying to pinpoint a wave in the ocean. You can tell where the crest is, but the wave stretches out across space. Similarly, a particle like an electron is described by a wave function, a scattered cloud of possibilities. If the wave is broad and smooth, you can't tell exactly where the particle is, but you can estimate its momentum reasonably well. If you narrow the wave to pinpoint the particle's position, the momentum becomes more uncertain. The wave gets choppy. It is a cosmic trade-off, and there is no way around it. The product of the uncertainty in position and the uncertainty in momentum is always greater than or equal to a tiny number. Planck's constant divided by 4p. This number is incredibly small, so in our everyday world the effect is negligible. You can measure the position and speed of a baseball with incredible precision without ever bumping into quantum limits. But at the scale of electrons, atoms, and subatomic particles, the uncertainty becomes impossible to ignore. It shapes the very behavior of the subatomic world. Confine a particle to a very small space to pin down its position, and it starts to behave wildly. Its momentum becomes highly uncertain, and it might start zigzagging unpredictably. Try to pin it down even further, and it resists even more. It is as if nature dislikes being told exactly where things are. This isn't a glitch in the machinery, it is a blur that cannot be erased. One way to think about it is like trying to hold mist in your hands. The tighter you squeeze, the less you have. Open your hands a little, and more of it remains. That is the delicate balance between knowing too much and being forced to let go of something else. In many ways, the uncertainty principle is a philosophical warning label. In the quantum world, it tells us that knowledge has borders, not because of human limitations, but because of how reality itself is constructed. We aren't dealing with tiny billiard balls rolling through space. We are dealing with possibilities, probabilities, and waves that refuse to be pinned down too rigidly. This principle also explains why atoms don't collapse. You might wonder why electrons don't simply fall into the nucleus of an atom, since opposite charges attract. But thanks to the uncertainty principle, electrons cannot sit perfectly still. If an electron fell into the nucleus and stayed there, its position would be perfectly known, which means its momentum would become infinitely uncertain, and that would require infinite energy. Nature says no. So electrons hover not because they want to, but because quantum rules allow nothing else. The uncertainty principle creates a sort of built-in resistance, a pushback against absolute confinement. This strange limit also has consequences for measurements of energy and time, or angular momentum and orientation. In every pair, increasing precision in one means surrendering certainty in the other. It is a universal truth at the quantum level. And yet, there is something comforting about it too. Uncertainty in this sense isn't chaos, it isn't uncontrolled randomness, it is a structured ambiguity, a kind of graceful blurriness. It gives texture to the universe, allowing particles to tunnel through barriers, atoms to be stable, and chemistry to happen. Without it, reality might be too rigid to support life. Much of science has been about finding certainty, predicting, measuring, knowing. Heisenberg's vision turned that desire upside down. He showed that some aspects of nature will always remain just slightly out of reach. And that isn't a failure, it is just how things are. In a strange way, the uncertainty principle invites us to make peace with not knowing, to sit quietly with the blur, and to appreciate the softness of what lies beneath the surface. It is a reminder that the deepest truths aren't always sharp but cloudy, undulating and unresolved. And perhaps that is exactly why they are so beautiful. In our everyday experience, things tend to be in one state or another. A coin lands heads or tails, a light switch is on or off, your tea is hot or cold, though sometimes questionably lukewarm. But in the quantum world, this neat division of states completely falls apart. Objects at the smallest scales don't always pick a side. They can hover in a strange middle ground, a mixture of all possible outcomes. This is the realm of quantum superposition. To visualize this, imagine flipping a coin in the classical world. Once the coin leaves your hand, it travels through the air with a clear trajectory. You might not know if it is heads or tails until it lands, but it is one or the other the entire time. It is just hidden from you. Quantum systems don't work this way. In the quantum world, if you flip a quantum coin, it doesn't secretly land on one side while you aren't looking. Instead, it enters a state of superposition, a weighted combination of heads and tails at the same time. It isn't undecided, it isn't rapidly flipping back and forth between the two, it is genuinely physically in a state that is both until you observe it. And when you do, when you check what state the system is in, the superposition collapses. The quantum coin chooses a face and your measurement becomes real. But before you looked, it wasn't just unknown, it was both. This is hard to swallow, and it isn't just counterintuitive, it is profoundly weird. Superposition was first introduced as a way to describe the behavior of quantum particles like electrons and photons. These particles, instead of following predictable paths, exist as wave functions, mathematical expressions that describe probabilities. Every possible state, a spin pointing up or down, a photon going left or right, is part of the equation, and all these possibilities coexist until a measurement selects one. You can imagine this as a foggy landscape of outcomes. The particle isn't tracing a path, it is more as if it is smeared out, blurring across all the possible routes it could take. When you interact with it, that mist suddenly snaps into a single location, a specific result like a lightning bolt illuminating a hilltop in the fog. This concept led to one of the most famous thought experiments in all of physics, Schrödinger's cat. Suppose you place a cat in a sealed box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector breaks the vial and the cat dies. If not, the cat lives. Quantum mechanics tells us that until the atom is observed, it exists in a superposition of decayed and not decayed states, and so by extension, the cat is simultaneously alive and dead until someone opens the box. This wasn't meant to be taken literally. Erwin Schrödinger was highlighting the absurdity of applying quantum rules to large objects, but the idea caught on. It portrayed superposition not just as an abstract idea, but as something with deeply strange implications for what reality is. And yet, despite all this weirdness, superposition isn't a flaw in the theory. It isn't some bizarre loophole that physicists tolerate. It is one of the most powerful features of quantum mechanics. In fact, much of modern quantum technology relies on it. Take quantum computing, for example. In a classical computer, the smallest unit of information is the bit, which can be 0 or 1. Everything your phone or laptop does, every photo, every song, every message, is encoded using combinations of these two states. Quantum computers use qubits, and a qubit, unlike a normal bit, can exist in a superposition of 0 and 1 at the same time. It isn't switching between them. It is genuinely in a mixture of both. This means a single qubit holds more information than a classical bit. And when multiple qubits are entangled, they can represent a vast number of states simultaneously. This allows quantum computers to perform certain calculations far more efficiently than classical ones. It isn't magic, it is just math playing by quantum rules. Problems involving complex systems, like simulating molecules or optimizing large networks, suddenly become tractable. And it all hinges on the ability of qubits to be in superposition. Superposition also appears in quantum cryptography, where it helps ensure that information cannot be intercepted without being noticed. In quantum sensing, it allows scientists to detect incredibly tiny changes in magnetic or gravitational fields. These aren't science fiction dreams, they are real technologies being developed right now. But there is a catch. Superposition is delicate. Quantum systems are easily disturbed. The slightest interaction with the environment, stray photons, vibrations, even air molecules, can collapse the wave function. This process, known as decoherence, is one of the biggest challenges in building stable quantum systems. It is like trying to balance a feather on the tip of a pencil while someone is sneezing in the next room. The superposition vanishes the moment the system interacts with the outside world. This fragility is part of what makes quantum systems so fascinating. They offer power, but only under very precise, isolated conditions. They give us access to probabilities, not certainties, and they ask us to rethink what it means to say that something is. This also leads to a deeper philosophical question. If particles can exist in multiple states, is that reality or just a reflection of what we know? Some interpretations suggest the wave function represents our knowledge, our best guess about a system until we measure it. Others say the wave function is physically real, and the particle truly is in multiple states until forced to choose. Either way, quantum superposition invites us to loosen our grip on classical logic. It tells us that opposites can coexist, that a system can be this and that, here and there, yes and no, all at once. That reality, in its essence, isn't a single thread, but a tapestry of overlapping, unresolved possibilities until observation pulls a loose thread. It is strange, it is uncomfortable, but it is also beautiful. Because in this strange rule of superposition, we find a universe that isn't rigid but flexible, not mechanical but poetic. It is a world that allows contradiction and uncertainty, not as flaws, but as features. And in doing so, it opens up new ways to compute, to communicate, to explore, and to imagine what is possible when reality refuses to make up its mind. Imagine you have two gloves, one for the left hand and one for the right. You put each glove in a separate box and send one to the other side of the world. You don't know which box contains which glove, but the moment you open one and see a left-handed glove, you instantly know the other must be right-handed. It isn't mysterious, it is just logic. The gloves were always a left and a right, no drama. But quantum entanglement isn't like that. Entangled particles aren't like pre-packed gloves. They are more like a pair of gloves that haven't decided which hand they are for until you open one of the boxes, and whichever one you open first somehow tells the other how to behave instantly. No matter how far apart they are, it isn't just that the results are correlated. It is that the properties don't seem to exist until the moment you measure one of them, and the act of measuring one instantly affects the other. This is the phenomenon of quantum entanglement, and it is one of the strangest and most unsettling features of the quantum world. Here is how it works. When two particles interact in a certain way, whether by being created together, colliding, or otherwise connecting, they can become entangled. This means their quantum states become linked. Whatever happens to one in a very real sense affects the other, even if they are separated by vast distances. Imagine creating two entangled photons whose polarizations are uncertain until measured. One might end up polarized vertically, the other horizontally, but they don't decide in advance who gets what. They remain in a shared quantum state, a superposition of all possibilities. Only when you measure one does the result become definite, and in that exact moment, the other's state also becomes definite instantly, with no signal, no delay, no chance to communicate. If you measure one photon in Paris, the other, let's say in Tokyo, responds at that exact moment, as if the universe just updated both simultaneously. This is what Einstein famously called spooky action at a distance. Einstein didn't like spooky things. He firmly believed in locality, the idea that physical processes in one place cannot instantly affect distant things. It is a pillar of relativity. Nothing, not even information, travels faster than light. The idea that two particles could coordinate results instantly without exchanging a signal made him deeply uncomfortable. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper challenging the completeness of quantum mechanics. They argued that if quantum mechanics allows such instant connections, it must be missing something, some hidden variables behind the scenes, determining the outcomes all along. For Einstein, the universe should be predictable, orderly, and perhaps most importantly, local. But decades later, experiments began to confirm what quantum theory had predicted all along. Entanglement is real, and those hidden variables never showed up. In the 1960s, physicist John Bell developed a testable mathematical inequality, now known as Bell's theorem, that could distinguish between quantum predictions and hidden variable theories. And when physicists ran these experiments repeatedly, quantum mechanics won. Entangled particles behave in ways that cannot be explained by local hidden variables. The results are random, but perfectly correlated. It is as if the particles share a private script, one that remains unwritten until the curtain rises, and they improvise together with eerily perfect timing. Still, this doesn't mean you can use entanglement to send messages faster than light. That would break causality, and fortunately, nature prevents it. Although entangled particles react instantly to each other's measurements, the outcomes are fundamentally random. You cannot control which result you get when you measure your particle, which means you cannot encode information into it. The instant connection is real, but it cannot be used for communication. It is like two people flipping coins on opposite sides of the galaxy. Each outcome is random, but somehow when one person gets heads, the other always gets tails, and neither knows what it will be until they flip. They aren't sending messages. They are just in sync in a way that defies space. What is truly strange is that this connection doesn't weaken with distance. You could separate two entangled particles by the width of a room, a continent, or a light year, and the entanglement would remain. There is no known limit. In fact, physicists have entangled particles over distances of hundreds of kilometers using satellites, and the results continue to confirm quantum theory. But what exactly is entanglement? Is it a sort of invisible string, a shared identity across space, a subtle form of information spread between particles? The truth is, no one is entirely sure. Different interpretations of quantum mechanics offer different perspectives. Some see entanglement as a reflection of information, what we know about the system, not the system itself. Others see it as evidence of a deeply non-local structure of reality. There is even a line of thought that entanglement isn't just a quirky quantum trick, but a fundamental feature of space and time itself. Some researchers have proposed that space-time, the very geometry of the universe, might emerge from networks of entanglement between tiny quantum bits. If true, entanglement isn't something that happens in space, it is what holds space together. That is a bold idea and still under investigation, but it suggests just how central entanglement might be, not just to particles, but to the very nature of reality. And like many quantum ideas, it isn't just theoretical. Entanglement has practical applications. It is the basis for quantum teleportation, not the Star Trek kind, but the actual transfer of quantum states from one place to another. It also underpins quantum key distribution, a method of secure communication that guarantees privacy. If a spy tries to intercept the key, the entanglement is disturbed, and the interference is immediately detectable. In quantum computing, entanglement allows complex operations involving many qubits that cannot be reduced to simple individual actions. It is part of what gives quantum computers their power, not just more speed, but more interconnection, a kind of parallelism that ordinary computers cannot match. So this spooky action, once a source of profound discomfort, is now a pillar of cutting-edge technology. Einstein might not have liked it, but even he couldn't deny its mathematical consistency. And while relativity and quantum mechanics haven't been fully unified yet, both remain astonishingly successful in their respective domains. Entanglement reminds us that the universe isn't simply a collection of independent objects bouncing around. It is a deeply interconnected web, where even distant elements can be part of a shared whole, where separation is sometimes an illusion. It isn't something we see in daily life. You don't wake up entangled with your neighbor or find your coffee reflecting the state of someone else's spoon, but at the most minute levels, this silent partnership between particles is quietly humming everywhere all the time. And perhaps that is the strangest part of all, that even in a universe of stars and silence, of vast distances and emptiness, there are still echoes of instant, invisible, and unshakable union. There are few animals in science more famous than Schrödinger's cat. This curious feline has become the unofficial mascot of quantum physics, a creature trapped in a thought experiment so peculiar that it is often mistaken for satire, and in a way it was. It was never meant to be taken literally, but like all good metaphors, it touches on something deeper, a quiet discomfort at the heart of quantum mechanics. The story begins in the 1930s when physicists were wrestling with what quantum theory actually meant. The math worked, the predictions were accurate, but what was it saying about the world? Was the wave function something real? Did particles truly exist in multiple states until measured, or was it just a tool for calculating outcomes? Erwin Schrödinger, already famous for his elegant quantum equation, was deeply skeptical of how far some physicists were willing to take the idea of superposition, especially when it came to measurement. In his view, there was something fishy about applying the same rules that governed electrons to everyday objects like, say, a cat. So he asked a question, a dark and playful one. What happens if you take the weirdness of quantum mechanics and scale it up to something you can hold in your arms? Imagine a sealed box. Inside the box is a cat. Next to the cat is a tiny radioactive atom, a Geiger counter, a vial of poison, and a trigger mechanism. If the atom decays, something quantum mechanics tells us happens randomly. The Geiger counter detects it, the trigger breaks the vial, and the poison is released. The cat tragically dies, but here is the twist. Quantum theory tells us that until we observe the atom, it exists in a superposition of decayed and not decayed states, which means the entire system, the detector, the poison, and yes, the cat too should be in a superposition. The cat is simultaneously alive and dead, not metaphorically, but literally, at least according to some interpretations. Of course, no one actually put a cat in a quantum box. Schrödinger wasn't proposing an experiment, he was making a point. He thought it was absurd to think that a cat, an animal with whiskers, warmth, and a clear preference for naps, could exist in such a blurry, undefined state. It wasn't just weird, it was nonsense. And yet the idea caught on, partly because it captured the essence of quantum indeterminacy in a single, unforgettable image. A cat that is both dead and alive until the box is opened. That is a powerful way to express what it means for a system to remain unmeasured. It isn't about indecision, it is about possibility until observation collapses the wave function. The system contains all outcomes, all futures, all states simultaneously. Schrödinger's cat isn't really about cats. It is about what we are allowed to say about the world before we look. In quantum mechanics, observation plays a central role. Before measuring a system, it exists in a cloud of probabilities, every possible state encoded in the wave function. But the moment you interact with it in a way that extracts information, that cloud collapses, the system chooses a state, one possibility becomes real and all the others vanish. But here is the tricky part. What exactly counts as a measurement? Is it the presence of a conscious observer, a mechanical detector, an interaction with the environment? Different interpretations give different answers, and that ambiguity is part of why the cat still gets so much attention. It forces us to confront the fact that quantum theory, while spectacularly successful at predicting outcomes, is strangely silent about what is actually happening along the way. Some physicists lean on the Copenhagen interpretation, which essentially says, don't worry about it. The wave function tells us everything we can know, and measurement simply reveals what is already latent in the system. Others prefer the many worlds view, where the cat is both alive and dead in separate branching universes, and opening the box doesn't collapse the wave function. It just selects your path through the multiverse. There is also the decoherence approach, which argues that interaction with the environment naturally filters out superpositions, leaving systems that appear classical. In this view, the cat is never truly in a state of limbo, just entangled with so many environmental variables that we can't track them all. The superposition becomes inaccessible, not non-existent. Every perspective carries its own philosophical baggage, but they all agree on this. Quantum systems don't behave like classical objects. In miniature, they don't sit still waiting to be discovered. They evolve probabilistically in complex, often counterintuitive ways. So what does this mean for the cat? It means the box isn't just a container, it is a boundary between the quantum and classical worlds, a stage where the rules of physics twist into something stranger, where questions like, is the cat alive, don't have simple answers. Instead, we have to say the cat is in a superposition of states, alive and dead, until we open the box and collapse that ambiguity into something definite. And that is what makes the cat a perfect metaphor for unmeasured systems in the quantum world. Systems evolve according to the Schrödinger equation, but that evolution doesn't pick a path. It explores all possible paths at once. An electron doesn't travel from point A to point B, it smears across all routes, all detours, until we observe it and reduce that blur to a single outcome. The cat in the box is just a macroscopic way to express this. The difference is one of scale, not principle, and that is what bothered Schrödinger, that the theory truly applies to everything. So, at some level, everything, including us, is part of a superposition, which leads to one final, somewhat unsettling question. What if the observer is part of the system? If opening the box collapses the cat's wave function, what collapses ours? Where does the line of the observer stop? Are we just another link in a long quantum chain, collapsing probabilities as we go, or are we simply surfing the wave of probabilities, never quite sure where the next collapse will take us? In the end, Schrödinger's cat isn't just about life and death, it is about knowledge and the strange dance between reality and observation. It is about what it means to say something is, when the very act of saying it can change the outcome. It is a reminder that in the quantum world, certainty is rare, clarity is conditional, and sometimes the universe waits for us to peek inside the box. In the everyday world, walls are pretty straightforward. If you throw a tennis ball at a wall and it doesn't have enough energy to break through, it bounces back. Simple, predictable. The universe says, "Nice try," and your ball obeys the rules of classical physics like a well-behaved object. But in the quantum world, predictability takes a vacation. In this strange realm, a particle can hit a wall, lack the energy to pass through, and yet appear on the other side without smashing, without breaking, without squeezing through cracks. It simply appears as if it decided the obstacle wasn't as solid as it seemed. This phenomenon is called quantum tunneling, and it is one of those effects that makes you blink, rub your eyes, and wonder if the laws of physics are playing a joke. But tunneling is very real. It is measurable, predictable, and fundamental to the functioning of the universe. And surprisingly, it all comes down to probability. To understand tunneling, we need to revisit the concept of wave functions. In quantum mechanics, particles like electrons aren't just tiny dots buzzing around. They are described by wave functions that represent a spread of possible positions. These waves can stretch across space, fading out gradually rather than stopping abruptly. This means that even if there is a region the particle technically shouldn't be able to reach, the wave function can still extend into that forbidden zone, albeit faintly. Now imagine a particle approaching a barrier, a region with more energy than the particle itself possesses. In classical physics, this would be a hard stop, game over. But the quantum wave function doesn't vanish at the barrier. It attenuates like a whisper fading through a wall. And if the wall isn't too wide or too high, that whisper can reach the other side. The particle might not have the energy to climb the barrier, but its wave function can tunnel through it. And if part of the wave function makes it to the other side, there is a small but non-zero probability that the particle itself will appear there too. It isn't magic, it is mathematics. This idea sounds abstract, but it has very concrete consequences, especially when you shrink your thinking down to the atomic scale. Take radioactive decay, for example. Some atomic nuclei are unstable, and one way they become stable is by ejecting particles like alpha particles made of 2 protons and 2 neutrons. These particles are trapped inside the nucleus by a powerful nuclear barrier. According to classical physics, they don't have enough energy to escape, but they escape constantly, and quantum tunneling is the reason. Inside the nucleus, the alpha particle's wave function stretches toward the edge of the nuclear potential barrier. Although unlikely, there is always a chance the particle will tunnel. Over time, that tiny probability accumulates, and eventually the particle appears on the outside. That is radioactive decay in action. Without tunneling, many elements would never decay, and nuclear physics as we know it would grind to a halt. Tunneling is also crucial for the most important energy source in the universe, nuclear fusion in the cores of stars. Hydrogen nuclei are crushed under immense pressure and heat, but even with these extreme conditions, they really don't have enough energy to overcome the electrostatic repulsion between their positively charged protons. According to classical calculations, fusion shouldn't happen nearly as often as it does, yet stars shine and tunneling explains why. At these high temperatures, hydrogen nuclei get close enough that their wave functions overlap, a small chance for one to tunnel through the repulsive barrier and fuse with another. Multiply that tiny chance by the unthinkable number of particles in a star, and you get a brilliant sustained fusion process. The furnace that powers everything from the sun's glow to supernovas. And it isn't just distant stars that benefit from tunneling. We use it right here on Earth, in labs, in factories, even in experimental computers. An elegant example is the Scanning Tunneling Microscope, or STM. This device allows scientists to visualize surfaces at the level of individual atoms. It works by bringing an ultra-sharp tip incredibly close to a material surface, just a few nanometers away. At that distance, electrons can tunnel between the tip and the surface. By measuring this tunneling current, the microscope builds an incredibly detailed map of the atomic landscape. The remarkable thing is that the STM doesn't touch the atoms. Its imaging relies entirely on tunneling, on the ability of electrons to silently slip through empty space, across a gap, and into a detector. This non-contact technique gives scientists a way to spy on the quantum terrain with stunning precision. Tunneling is also at the heart of certain electronic components like tunnel diodes and quantum dots, and it is a looming factor in the future of computing. As we shrink transistors to smaller and smaller sizes, we are hitting quantum limits. At nanometer scales, electrons can tunnel through barriers that were once considered solid. It is as if the walls in our circuits are starting to let particles escape when they shouldn't. This presents both challenges and opportunities. On one hand, it creates noise and unpredictability in traditional electronics. On the other hand, it opens the door to quantum technologies that use tunneling instead of fighting it. At its core, tunneling teaches us something profound about the nature of reality. We often think of the world as made of rigid boundaries. A particle can go here, but not there. A wall is a wall, but the quantum world is more subtle. Barriers aren't impenetrable, they are probabilistic. They are suggestions, not absolutes. And while we might find this unsettling, it is also strangely elegant. Because of tunneling, particles aren't confined to the straight paths we imagine. They can cheat, slide, blur through the cracks of logic. They remind us that the universe isn't a machine made of perfect gears, but a shimmering tapestry of probabilities and possibilities. The tennis ball still bounces off the wall, but the electron, the alpha particle, the photon, they can just look at that same wall and say, "I think I'll take the shortcut." And somehow nature allows it. In daily life, we think of nothing as well, nothing. The absence of things, an empty room, a blank sheet of paper, the space under your bed where socks mysteriously vanish. And when we extend this idea to physics, we often imagine the vacuum of space as a perfect void, a cold, silent expanse with absolutely nothing in it. But in quantum physics, nothing is never truly empty. What we call the quantum vacuum is a restless, vibrant stage. It isn't filled with atoms, light, or sound, but it is far from blank. Even when all particles are removed and no fields are actively doing anything, the vacuum still boils with energy. At the smallest scales, space is alive with invisible activity, waves rising and falling, particles blinking in and out of existence. It is like the hum beneath the silence, the glow behind the darkness, and it all starts with uncertainty. Heisenberg's uncertainty principle doesn't just apply to the position and momentum of particles, it also applies to energy and time. This means that even in a region of space where energy should be zero, energy can briefly fluctuate. These fluctuations give rise to virtual particles that spontaneously appear, linger for a fleeting moment, and then vanish as if they never existed. They are called virtual not because they are imaginary, but because they cannot be observed directly, only inferred through their effects. These quantum blips might seem like a mathematical curiosity, but they have very real consequences. One of the most striking examples is something called the Casimir effect. It is one of those rare phenomena that lets us see the quantum vacuum doing something tangible, something measurable. Here is how it works. Imagine placing two very thin, perfectly conducting metal plates extremely close to each other in a vacuum, just a few nanometers apart. According to classical physics, nothing should happen. There are no forces, no push or pull, just empty space. But quantum mechanics says otherwise. Because the space between the plates is so small, only certain wavelengths of virtual particles can exist there, those that fit perfectly between the boundaries. Outside the plates, however, there is no such restriction. The result? There is slightly more pressure from virtual particles outside the plates than between them, and this imbalance creates a force that pushes the plates together. That is the Casimir effect. It is a tiny force, but it has been measured. In precise laboratory experiments, scientists have observed these plates attracting each other exactly as quantum theory predicts. It is as if the vacuum itself is gently squeezing them, proving that even nothingness has a sort of substance. This vacuum energy isn't limited to quirky lab setups. It plays a role across the entire universe. In cosmology, there is the idea of vacuum energy density, the notion that the energy of empty space might be responsible for the accelerated expansion of the universe. We call this mysterious force dark energy, and while we don't fully understand it, the concept of a quantum vacuum humming with energy could be a large piece of the puzzle. But there is a catch. The predicted energy of the quantum vacuum, according to quantum field theory, is enormous. If we tried to calculate the total vacuum energy of the universe using what we know of particle physics, we would get a number wildly larger, some 120 orders of magnitude larger than what we actually observe. This is often called the worst prediction in physics, and no one has figured out how to fix it, but it highlights just how complex and surprising the vacuum truly is. Back at the quantum scale, virtual particles also play a supporting role in other strange phenomena. In quantum electrodynamics, for instance, the interaction between charged particles is partially mediated by the constant exchange of virtual photons. These exchanges give rise to the electromagnetic force as we experience it. Even the mass of particles like protons is affected by the swarm of virtual quarks and gluons blinking inside them. What we think of as solid stable matter is actually the result of constant interactions with this invisible fluctuating vacuum. And while these particles pop in and out faster than we can measure, there are influences everywhere. They slightly alter the energy levels of electrons in atoms, contribute to the magnetic moment of particles, and are woven into the fabric of every interaction in nature. This might sound like science fiction, but it has been tested. When we correct our calculations to include vacuum fluctuations, like in the famous Lamb shift observed in hydrogen atoms, we find the predictions match reality with breathtaking precision. The math is weird, the concepts are wild, but the results are solid. In a way, the quantum vacuum is the most fundamental field of all. All other fields, electromagnetic, gravitational, nuclear, exist within it. They ripple and hum against its backdrop like instruments playing over a bass line that never stops. Some physicists even suspect the vacuum holds clues to deeper truths. It could be the source of all structure in the universe. It might contain information about quantum gravity or even about space-time itself. These are open questions, but one thing is clear: the vacuum isn't a passive backdrop. It is active, structured, and full of potential. Even in the coldest regions of space, where matter is scarce and starlight is a memory, the quantum vacuum is still there, vibrating, trembling, whispering the rules of existence to anything willing to listen. It is humbling to think that nothing is never truly nothing, that even in the apparent stillness the universe teems with hidden activity in the pauses between the moments, in the gaps between particles, in the silence between the stars. Something is always happening. We live not on a silent stage, but one that murmurs beneath our feet. And while we can't hear it with our ears, physics has found the instruments to listen. The vacuum hums, particles blink, and reality dances. There is a rhythm we are only just beginning to understand. In the quantum world, reality doesn't always behave like a story with a clear beginning, middle, and end. Particles don't just travel in straight lines. They drift in clouds of probability. They superpose, entangle, and sometimes tunnel through things that should be solid. But perhaps the most mysterious twist in this quantum tale comes when we ask a very human question: what happens when we look? This simple act of observing, of measuring, seems to trigger something dramatic, a change in the very nature of the quantum system. This is known as wave function collapse. Before measurement, a particle, like an electron or a photon, is described by its wave function, a mathematical object containing all the possible outcomes of where it could be or how it could behave. That electron isn't in one place, it is in a mixture of many possible places. Its spin isn't up or down, it is both. Its path isn't chosen, it is all of them at once. The wave function is a shimmering probabilistic mist, but then you measure it. You turn on your detector, you ask, "Where are you?" And in that instant, the wave function collapses. The mist condenses. All those swirling possibilities snap into a single reality. The electron is suddenly right there at a precise point. Its spin is up or down, not both. And this collapse doesn't seem to happen gradually. It isn't a slow fading of possibilities. It is abrupt, binary. One moment the system is in superposition, the next it is locked into a definite state, as if the universe, after much hesitation, makes a final decision the moment we check. It is strange enough on its own, but it gets weirder because no one knows exactly what causes the collapse. Is it the physical interaction with a measuring device? Is it the transfer of information? Is it consciousness, a camera, a fly buzzing in the lab? The truth is, wave function collapse, while central to quantum theory, is not well understood. It might be the greatest mystery in all of modern physics. Different interpretations of quantum mechanics try to answer the question in different ways. The most traditional view is the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. In this view, the wave function isn't a real physical object, it is just a tool for predicting probabilities. And the collapse happens when a measurement is made, when we gain information. Before that, asking about what is really happening is meaningless. The electron isn't somewhere waiting to be found. It simply isn't anywhere in particular until we look. It is a practical approach. It makes the math work, but it leaves many scientists dissatisfied because it doesn't really explain what measurement is or why the wave function should collapse. Then there is the many worlds interpretation, which throws collapse out the window. According to this idea, the wave function never collapses. Instead, every possible outcome happens, just not in your universe. Measure the spin of an electron, and the universe splits. In one version, it is spin up, in another, spin down. You only experience one of these outcomes, but the others still exist, unfolding in parallel. No collapse, no mystery, just branching realities. It is a bold idea, surprisingly consistent with quantum math, but it comes at the cost of multiplying universes like cosmic confetti. Every measurement, every interaction, every choice, an endless spray of realities. It is elegant in one sense, absurd in another. Other interpretations aim to make collapse more real. In objective collapse theories, the wave function is a physical thing that collapses spontaneously, randomly, without measurement, though measurement increases the chance of collapse. These theories introduce new rules or even new physics to explain when and how collapse happens. They are still being tested, but they offer an intriguing possibility that wave function collapse might be something nature does, not just something we see. Then there is cubism, a newer, more radical view suggesting the wave function doesn't describe the system, it describes our beliefs about the system. It is a personal, subjective tool for predicting outcomes, and collapse isn't a physical event but a mental update, like learning a new fact and revising your expectations. Reality doesn't change, you do. Some physicists find this refreshing, others find it deeply unsatisfying. After all, shouldn't physics be about the universe, not our opinions? There is also the role of decoherence, which doesn't explain collapse directly, but helps describe how superpositions seem to vanish in large systems. When a quantum system interacts with its environment, even with just a few stray photons, it becomes entangled with the world around it. This entanglement causes the interference patterns we associate with superpositions to fade away for us. The system looks like it collapsed, even if it hasn't actually chosen a state. Decoherence explains why cats don't stay alive and dead at the same time, but it stops short of saying how a single outcome becomes real. And so here we are. More than a century after the birth of quantum theory, wave function collapse remains a ghost in the machine. The math works brilliantly. We can predict outcomes with incredible accuracy. But what exactly collapses, when, and why? Is collapse even real, or are we just seeing the limits of our own understanding? Ideas are not lacking. Some researchers believe we need a new theory of measurement or a deeper theory of reality that goes beyond quantum mechanics. Others are content with the ambiguity, saying the predictions work and the rest is philosophy. But philosophy matters, especially here, because the question of wave function collapse isn't just about particles, it is about what the universe is. Is reality fundamentally probabilistic, observer-dependent, constantly branching, shaped by information, by consciousness, by something we haven't discovered yet? And how much can we truly know? You can think of collapse as the moment the quantum world transitions into the classical, a sort of phase change, like water freezing into ice. But unlike water, the rules of this transformation are obscure. We don't know the temperature, we don't know the pressure. We just know that at some point the mist becomes a shape and possibility becomes presence. It is easy to get lost in metaphors. The wave function is a veil, a dream, a menu of futures waiting to be chosen. Perhaps it is all of these and none of them. Perhaps what collapses isn't the wave function itself, but our illusion that the world must always be definite, always one thing or another. Perhaps the universe is content to be undecided. Perhaps it is we who insist on conclusions. What happens when we measure? Maybe the better question is, what do we think happens? And are we prepared for the answer to be stranger than we expected, but truer than we imagined? If quantum physics had a hometown, it would probably be Copenhagen. Not because of the scenery, though Denmark has a charming supply of windmills and bicycles, but because it was there that some of the strangest ideas in physics were seriously discussed, debated, and quietly accepted. At the heart of this story is Niels Bohr, a Danish physicist with a gentle demeanor and a taste for long, complex sentences. Bohr helped shape one of the most influential views of quantum mechanics, a perspective that became known as the Copenhagen interpretation. The idea is deceptively simple. In fact, that is part of its charm. According to the Copenhagen view, quantum systems don't have defined properties until they are measured. An electron doesn't have a fixed position. A photon doesn't commit to a specific polarization. A particle doesn't choose a state until an observation forces it to. Before measurement, reality is a blurry cloud of possibilities, a wave of probability. Measurement doesn't just reveal something that was already there, it creates the outcome. In other words, reality isn't quite real until we observe it to be. This is a bold claim, and it is the kind of thing that makes philosophers sit up and physicists reach for coffee. But Bohr and his colleagues weren't trying to make the universe mysterious for its own sake. They were trying to make sense of experimental results. Every time they tried to treat particles like tiny billiard balls, the math fell apart. But when they treated particles as probability waves that only resolve upon measurement, things clicked. The wave function in this view isn't a physical thing. It doesn't describe the actual position or momentum of a particle. Instead, it encodes everything we can know about the system. It is a mathematical catalog of possibilities, not a map of what is. This leads to one of the central claims of the Copenhagen interpretation. Questions about the state of a system before measurement are meaningless. Asking where the electron was before you measured it makes no sense, because where only becomes a meaningful concept after measurement. Reality isn't something you uncover like a curtain. It is something that comes into focus the moment you look. It isn't that the particle was hiding its true nature, it simply didn't have one yet. Understandably, not everyone found this satisfying. Albert Einstein, for instance, was famously uncomfortable with the idea. He wanted a universe that existed independently of anyone looking at it. He believed in an underlying, objective, deterministic reality, even if it was currently hidden. To Einstein, the Copenhagen interpretation sounded like saying, "The moon doesn't exist unless you are looking at it." Bohr disagreed, but he didn't try to offer a grand metaphysical solution. Instead, he embraced a sort of pragmatic ambiguity. His position was that quantum theory tells us what we can say about nature, not necessarily what nature is. The role of science in this view isn't to discover what is really out there, but to describe the results of experiments as accurately as possible. If that sounds a bit unsatisfying, you aren't alone. The Copenhagen interpretation is often accused of being more of a prescription than a description. It tells you how to use the equations. It tells you what the outcomes will be, but it doesn't tell you what is actually happening behind the scenes. This gave rise to the now infamous phrase, "shut up and calculate." It isn't a quote from Bohr himself, but it captures the sentiment of many practicing physicists. The idea is to stop worrying about the metaphysical implications and just use the theory. It works, it gives correct predictions. Isn't that enough? And to be fair, the Copenhagen approach does work. It is the standard interpretation used in countless textbooks, labs, and classrooms. It underpins the design of semiconductors, lasers, and quantum computers. It has never failed an experimental test. For many scientists, that track record outweighs any philosophical discomfort, but still the discomfort persists. If reality only becomes real when measured, what does that say about the universe before observers existed? Did nothing have defined properties? Before conscious life arrived, was the early universe in a sort of suspended animation, waiting for someone to look? Most physicists would say no. The Copenhagen interpretation doesn't require a conscious observer, just an interaction with a measuring device or the environment. Observation in this context is just a process of extracting information from a quantum system in a way that forces it to pick a side. But even that leads to more questions. What counts as a measurement? At what point does the wave function collapse? Why does the universe follow this strange rule? The Copenhagen camp tends to answer with a shrug and a smile. The theory doesn't explain why collapse happens. It just says when. If you want a deeper explanation, you will have to look elsewhere, and many have. Competing interpretations like many worlds, pilot wave theory, and objective collapse models aim to offer a more complete picture. Each tries to preserve some classical intuition, that reality exists independently, that cause leads to effect, that observation gets no special treatment. But each of these alternatives comes with its own complications. Copenhagen, by contrast, is lean. It doesn't introduce hidden variables, it doesn't multiply universes, it just establishes a set of rules. Calculate the wave function, apply the measurement postulate, and predict the outcome. Simple, direct, effective. Perhaps that is its appeal. In a field full of strange possibilities, the Copenhagen interpretation offers a sort of calm. It isn't trying to solve every mystery. It is content to describe the world we can see, measure, and interact with, without pretending to know the deeper machinery behind the curtain. And perhaps that is enough. Bohr often spoke in layered, almost poetic language. He once said, "Those who are not shocked when they first come across quantum theory cannot possibly have understood it." He understood that the Copenhagen approach wasn't about making peace with reality, it was about making peace with uncertainty. Quantum mechanics is weird, but instead of struggling to make it neat, the Copenhagen interpretation invites us to accept that weirdness and work within it, without demanding that the universe explain itself. It isn't a final answer, it is a quiet rulebook, a reminder that in the quantum world, simplicity and discomfort often travel together, and that sometimes the best we can do is shut up and calculate. Imagine you are holding a coin between your fingers. You flip it, it spins in the air, catching the light, and lands with a soft click. Heads. But according to one interpretation of quantum mechanics, something else also happened. Somewhere not here, but still real, the same coin landed tails. And in another place still, it landed on its edge, rolled off the table, and stopped under the sofa. Every possible outcome of that flip unfolded. Not as a maybe, not as a probability, but as a real branch of reality, and you simply find yourself in the one where you saw heads. This is the strange and elegant idea behind the many worlds interpretation. Quantum physics began as a thought experiment, an alternative way of looking at the infamous problem of wave function collapse. You will remember the wave function, the mathematical cloud of probabilities that defines everything about a quantum system. In the traditional Copenhagen view, when you make a measurement, the wave function collapses, and one possibility becomes real. But what if it never collapsed? In 1957, physicist Hugh Everett III proposed a radical idea. Perhaps the wave function is always evolving smoothly and deterministically. Perhaps when you measure a system, you don't force it to choose a single outcome. Instead, you split. The universe splits. Every possible outcome happens, but each in its own branch, separate from reality. It sounds dramatic, like something out of science fiction. But Everett wasn't writing a novel. He was doing math, and his version of quantum mechanics is mathematically identical to the standard version, just without the extra rule that says collapse happens when you observe. In his view, the wave function never collapses, it just branches. Here is how it works. Imagine an electron with two possible spin states, up and down. If you measure its spin, classical quantum mechanics says the electron is in a superposition of both states until measured, at which point it chooses one. Everett said instead that the measurement causes the system and the observer to split into two correlated branches. In one, you observe spin up, in the other, spin down. Both outcomes are real. Both versions of you exist, each in a different branch of the universe. No randomness, no collapse, just a growing, branching tree of reality. This might sound like a recipe for science fiction overload. Parallel universes, doppelgangers, infinite copies of everything. But the many worlds interpretation isn't based on fantasy. It doesn't propose new physics or untested forces. In fact, its main appeal is that it sticks to the math we already use. It simply refuses to add the extra assumption that something magical happens when you look. For many world supporters, this is its strength. The idea is strange, but the math is clean. Of course, not everyone is comfortable with it. For starters, if the universe is constantly branching into new realities, where do all those universes go? Are they stacked on top of each other, floating in some higher dimensional multiverse? The theory doesn't say, and that is part of the philosophical tension. Many worlds isn't a theory about the structure of space. It is a statement about how quantum systems evolve. The other branches are real, but they don't interact with ours. Once a split occurs, the branches decohere, which means they no longer interfere with each other. They become, for all practical purposes, invisible. This makes the theory hard to test directly. After all, if we can't observe the other branches, how do we know they are there? That is the central criticism. Many worlds might be elegant, but is it falsifiable? Can you prove it wrong? Supporters argue that is the wrong question. They say it isn't about adding new predictions, but about not adding unnecessary assumptions. If the wave function evolves smoothly according to the Schrödinger equation, and that equation never includes collapse, why assume collapse exists? Occam's razor, often paraphrased as the simplest explanation, is usually correct, cuts both ways here. Copenhagen keeps the universe small by adding collapse. Many worlds keeps the math simple by accepting a very large universe. But is this universe too large? Let's take a quiet moment to imagine the scale. Every time a quantum interaction has multiple possible outcomes, the universe branches. This includes not just lab experiments, but molecular collisions, radioactive decays, photon emissions, and everything else. The universe isn't splitting occasionally, it is branching constantly, exponentially, unimaginably. But just as we don't feel the earth spinning beneath our feet, we don't feel the branching. To us, it is invisible, continuous. We simply see one outcome as if it were all that ever existed. It is also important to say that in many worlds, these other realities aren't parallel lives in the sci-fi sense. You aren't jumping between them. You don't meet your other selves eating soup instead of salad. Each branch is causally isolated from the others. There is no communication across the split, no peeking into other versions of yourself. Once a split happens, it is permanent. This avoids many of the philosophical headaches that come with wave function collapse. There is no need to define what counts as a measurement or when reality becomes real. Everything evolves smoothly. Measurement is just entanglement. You and the system become linked, and the world unfolds accordingly. But this calm elegance also has a cost. If every possible outcome happens, then why do we feel like only one outcome occurred? Why does it seem like the coin landed heads and not tails? If all outcomes are real, what does probability mean? Many worlds redefines probability not as the chance of something happening, but as a measure of how many of you end up in each branch. It is a subtle shift. Instead of asking what the odds are, you ask, what fraction of my future self see this outcome? It isn't intuitive, but quantum mechanics in general isn't either. And despite all its strangeness, many worlds has inspired deep, serious research. Some physicists believe it could help unify quantum mechanics with gravity. Others see it as a foundation for understanding quantum computing, where superpositions and entanglements do the heavy computational lifting across possible states. It also offers a unique kind of comfort or discomfort, depending on your perspective. In this interpretation, no outcome is truly lost. Every possibility exists somewhere. The decisions you didn't make, the chances you didn't take, are all still there, unfolding in parallel timelines, not just as hypotheses, but as real physical events. Many worlds isn't meant to make you feel small. If anything, it is a reminder that the universe might be more generous than we imagined. Not just a single story unfolding, but a vast shimmering library with every possibility recorded in existence. So, when you think of many worlds, don't imagine a noisy stack of cartoon realities. Imagine a quiet branching tree, each branch a path, each leaf a world, each outcome a poem written in the language of physics, and all of them in their own way true. Imagine pulling back the curtain on everything, the stars, the oceans, your chair, your hand, even the light falling softly on your pillow. What if all of it, all matter and energy, wasn't made of solid stuff, What if the most fundamental stuff of reality wasn't matter at all, but vibrations, waves, invisible ripples spreading through fields that fill all of space? Welcome to the silent, deeper world of quantum field theory, where the universe isn't built with particles but with fields that shimmer beneath. Let's start gently. In classical physics, a field is something that assigns a value to every point in space. A familiar example is the electric field, an invisible force that tells a charged particle how it should move. If you place a positive charge in an electric field, it feels a push. That is the field in action. Fields are smooth, continuous, and fill the universe like invisible jelly. Now quantum mechanics arrives and sprinkles uncertainty over the picture. It says fields don't just sit still, they fluctuate, they hum even in the absence of real particles. Every field, electric, magnetic, gravitational, is quantum in nature. It vibrates even when it seems empty. Even the vacuum, as it turns out, isn't truly calm, it is restless. And here is the leap. In quantum field theory, or QFT, everything is a field. Every particle you have ever heard of, electrons, photons, quarks, neutrinos, is just a tiny blip in its corresponding field. A particle isn't a little hard ball flying through space. It is a localized ripple, a bump, an oscillation in an underlying field that fills all of reality. Let's take the electron. Somewhere in space exists the electron field, a quantum field that exists everywhere. When you see an electron, you aren't looking at a separate, autonomous object. You are observing a specific quantized excitation of that field. The field got excited in a localized way, and that is what you call an electron. The same goes for photons. The electromagnetic field fills all of space. When a particle of light goes buzzing by, it isn't a tiny bullet. It is a ripple, a tiny vibration in the electromagnetic field. Turn the dial on that ripple the right way, and you get visible light. Turn it differently, and you get microwaves or X-rays. But it is all just dance moves in the same field. There is a field for every known particle: quark fields, gluon fields, Higgs fields. Even the elusive graviton, if it exists, would be a ripple in the gravitational field. So where did our old friend the particle go? In a sense, particles are a useful fiction, a way to describe the behavior of fields in certain contexts. When the field is localized and the ripple behaves like a discrete packet of energy, it is convenient to call it a particle, but that is just our label for a behavior. The field is fundamental, the ripple is what we see, but the field is what is actually there. This shift in perspective is profound. It transforms the universe from a Lego set made of tiny blocks into something more like a symphony, an infinite orchestra of overlapping notes, with reality emerging from their interference and harmony. Quantum field theory also explains some intriguing features of quantum mechanics that standard quantum theory struggles with. For example, how do particles create and destroy themselves in high-energy reactions? Simple. They are just field excitations. Pump enough energy into a region of space, and you can agitate a field hard enough to spawn a new ripple. That is how particle collisions in places like CERN can produce entirely new particles out of what seems like thin air. And antiparticles, the dark twin of the electron, the positron? In quantum field theory, antiparticles are just another mode of excitation in the same field with opposite properties. Nothing ghostly, just more symmetries in the ripple. Here is a particularly elegant twist. Forces themselves are mediated by fields. The electromagnetic force is the result of charged particles exchanging photons, ripples in the electromagnetic field. The strong force is gluons vibrating in the gluon field, binding quarks. Gravity, if it is ever successfully quantized, would involve tiny ripples in the gravitational field, gravitons. Even empty space isn't truly empty. Quantum field theory predicts that fields are never completely still. They are always vibrating with vacuum fluctuations. These fluctuations can have measurable effects, like the Casimir effect, where two metal plates placed very close together in a vacuum feel a force pulling them, caused by changes in the field energy between them. There is something wonderfully serene in this picture, the idea that space itself isn't a passive backdrop, but an active participant. Every point in space is alive with potential. Every particle, every interaction, every beam of light or burst of energy is just the field expressing itself. Of course, quantum field theory is complicated. It isn't something you can casually calculate on a napkin unless your napkin is the size of a chalkboard and your chalk is labeled Feynman diagrams. But the conceptual takeaway is elegant. Nature, at its most fundamental level, isn't made of things. It is made of excitations, patterns, energy organized in space and time. Even mass, the stubborn, heavy quality of matter, is in many cases an emergent feature of field interactions. The Higgs field, discovered experimentally in 2012, is responsible for giving mass to many particles. Particles interact with this field like swimmers moving through molasses. The more resistance they feel, the more mass they seem to have. So here we are, nestled in a world of fields. You, as you listen to this, are a delicate pattern in the electron field, the quark field, the photon field. Your thoughts are patterns of excitation. The very atoms of your body are knots in a cosmic mesh of fields humming in invisible harmony. You don't end at your skin. The fields that define you stretch across the universe. There is no sharp edge, no hard boundary, just smoother or stronger ripples fading into the wider sea of quantum reality. Quantum field theory doesn't just describe the universe, it is the universe, or at least it is the best map we have drawn so far. A map where reality isn't made of things bumping into each other, but of fields intertwined in a dance too fast, too subtle, and too beautiful to be fully captured. And if you are still awake, you might be wondering, if everything is a ripple in a field, what are we rippling through? That, dear listener, is a question for another dream. If the universe came with a recipe, the standard model of particle physics would be its ingredient list, minus a few mysterious spices like dark matter and dark energy. It is a surprisingly compact recipe, elegant in its organization and a bit chaotic in its naming conventions. But despite its quirks, this model is one of the most successful theories in the history of science. It tells us what the universe is made of, how those parts interact, and why matter behaves the way it does. Let's start by introducing the cast. At its core, the standard model is a collection of elementary particles. Particles that, as far as we know, cannot be divided into anything smaller. You can think of them as the fundamental building blocks of matter and force, woven together by the threads of quantum fields. There are three big families: quarks, leptons, and bosons. Quarks are the stuff protons and neutrons are made of, the solid core of atoms. There are 6 types or flavors of quarks: up, down, charm, strange, top and bottom. Yes, those are their real names. Physicists can do the most precise math imaginable, but when it comes to naming, that is where the chaos blooms. The up and down quarks are the lightest and most common. A proton is made of 2 up quarks and 1 down. A neutron is made of 2 down quarks and 1 up. This means everything you see, touch, or are is mostly up and down quarks. But then there are the electrons, which we will meet in a moment. The other quarks, charm, strange, top, and bottom, are heavier, rarer, and mostly show up in high-energy environments like particle accelerators or cosmic rays. They are like the special guest stars of the particle world, flashy, short-lived, but important in the grand scheme. Next, we have the leptons. This group includes the electron, which you have met many times buzzing around atoms, carrying electricity and generally making life possible. Electrons also have cousins. There is the muon, which is like a heavy electron, and the tau, which is even heavier. Like the exotic quarks, these heavier leptons don't last long in nature, but they appear in high-energy reactions and leave distinct traces. Each of these charged leptons comes with a neutral partner, the neutrino. There are 3 of them, one for each flavor, and they are incredibly light, incredibly fast, and incredibly aloof. Neutrinos barely interact with matter. Billions pass through your body every second, leaving no trace. They are the introverts of the universe, always present, rarely noticed. So far we have 6 quarks and 6 leptons arranged in 3 organized generations. That is 12 matter particles in total, all dancing on a stage set by quantum fields. But matter alone doesn't make a universe. We need forces, the rules that govern how these particles interact. That is where the bosons come in. Bosons are the force carriers. Every fundamental force has its own messenger particle, a sort of quantum handshake that tells the other particles what to do. For the electromagnetic force, the carrier is the photon, the particle of light. It has no mass, moves at the speed of light, and keeps electrons bound to atoms. Without photons, chemistry and breakfast wouldn't exist. The weak nuclear force, responsible for processes like radioactive decay, has 3 bosons, the W+, W-, and Z. Unlike the photon, these are heavy, so heavy in fact that they are only involved in interactions at very short distances. They help turn neutrons into protons and vice versa, powering the fusion that drives stars. Then there is the strong nuclear force, the glue that holds quarks together inside protons and neutrons, and binds those protons and neutrons inside atomic nuclei. Its carrier particle is the gluon, a massless, highly energetic force carrier that comes in 8 varieties. Gluons are like a very excited group of toddlers in a ball pit, constantly exchanging energy, never sitting still, and entirely responsible for your atoms not flying apart. Finally, the newcomer, the Higgs boson. This particle was confirmed experimentally in 2012 at CERN and won a Nobel Prize the following year. The Higgs boson is the manifestation of the Higgs field, which permeates space and gives mass to many of the other particles. Without the Higgs mechanism, the standard model would describe a very strange world, one where most particles would buzz around massless, unable to clump together into atoms. So, to recap, we have 12 matter particles, 6 quarks and 6 leptons, and 5 force-carrying bosons: photon, W, Z, gluon, and Higgs. That is the standard model, and it works beautifully. This model has predicted the outcomes of countless experiments with astonishing precision, from the behavior of particles in colliders to the decay rates of radioactive isotopes. The standard model keeps getting it right. It isn't perfect, but it is remarkably stubbornly good at what it does. Of course, it has some gaps. For starters, it doesn't include gravity. The standard model is a quantum theory, while gravity is best described by Einstein's general relativity, a classical theory. Uniting these two frameworks is one of the greatest unsolved problems in physics. Then there is dark matter. Astronomical observations suggest that most of the matter in the universe is invisible and doesn't interact with light. The standard model doesn't explain it. None of its particles can account for the gravitational effects we see in galaxies. And let's not forget dark energy, the mysterious force driving the accelerated expansion of the universe. That is also outside the standard model's jurisdiction. In fact, the standard model only describes about 5% of the universe. But what a 5%! Every atom, every interaction, every burst of light, every breath you take is contained in this shimmering trellis of particles and forces. It is often said that the standard model is complete, yet unsatisfying. It is like finishing a jigsaw puzzle only to realize the picture on the box was just a small section of a much larger image. But still, what is there is impressive. Elegant symmetries, intricate relationships, and mathematical structures that link particles in ways that suggest a deeper unity. Some theorists suspect that all of this, quarks, leptons, bosons, might one day be unified under a grand unified theory or even a theory of everything. Those dreams might be beyond the reach of current experiments, but they are guided by the same spirit that built the standard model, the belief that nature is knowable, that patterns lie beneath the chaos, and that even the wildest forces obey silent laws. So, the next time someone asks what the universe is made of, you can smile and say mostly quarks, some leptons, and a handful of bosons. And then for fun you can add, oh, and don't forget the Higgs field. Without it, none of this would have weight. It isn't the whole story, but it is a good opening chapter. At the intersection of dazzling complexity and mathematical perfection lies a theory that might be the crown jewel of physics, quantum electrodynamics, or QED for short. It is the framework that explains how light and matter interact, and it does so with such precision that even the most demanding decimal places are left in awe. At its core, QED describes the quantum dance between electrons and photons. Every flicker of light, every spark, every push and pull between charged particles is a performance choreographed by the rules of QED, and somehow, despite involving an infinite number of possible interactions and mind-bending probabilities, the final answers it gives match experiments with ridiculous accuracy. We are talking about predictions confirmed to better than 1 part in a billion. It is like measuring the width of North America to the precision of a human hair and being right. So, how does QED pull this off? Let's start with the problem it solves. In the early 20th century, physicists knew electrons interacted with the electromagnetic field. When an electron accelerates, it emits light. When it absorbs light, it changes energy levels, but calculating the exact behavior of these interactions at the quantum level proved to be a nightmare. The equations blew up. Infinities appeared where they shouldn't. You tried to calculate how an electron emits a photon, and the math spat out absurdities like infinite energy, which isn't helpful unless you are trying to cook the entire universe. Enter a physicist with a mischievous smile and a love for good taste, Richard Feynman. Feynman, along with Julian Schwinger and Shinichiro Tomonaga, found a way to make QED behave, but Feynman went a step further. He made it visual. He invented Feynman diagrams, a graphical way to represent particle interactions that turned complicated quantum calculations into almost childlike scribbles. In these diagrams, particles are lines. Time flows from left to right. An electron can enter from one side, emit a photon, and continue on its way. That photon can go buzzing off and hit another electron, or loop around and affect the same one. Each of these paths has a mathematical expression, and QED tells you to sum them all up, not just the most likely one, but every possible way the interaction could happen. This includes some pretty wild possibilities. An electron emits a photon that becomes an electron-positron pair, which then annihilates and becomes another photon that is absorbed again. These are known as virtual particles. They exist only in the mathematical interludes between real, measurable events, but they shape the outcome in very real ways. This is where QED becomes less like physics and more like poetry written in calculus. It doesn't just account for what happens, it accounts for everything that could happen. Every zig, every zag, every loop and scribble is part of the final answer. And somehow, when all these possibilities are woven together, the result is a prediction so precise it could tell you how an electron would behave on the other side of the galaxy down to the last decimal place. One of QED's triumphs is its explanation of the anomalous magnetic moment of the electron. The electron has a tiny magnetic field like a miniature magnet. Classical physics predicts its strength, but quantum effects tweak it just a little bit. QED calculates this tweak and matches the experimental result to more than 10 decimal places. It isn't just good, it is staggering. The theory also elegantly explains phenomena like Compton scattering, where a photon bounces off an electron, Bremsstrahlung, where a particle emits radiation as it slows down, and pair production, where light can turn into matter and antimatter. All these processes that sound like sci-fi spells arise naturally from the framework of QED. It is worth mentioning that QED isn't alone. It is the quantum field theory that describes electromagnetism, but it is also the prototype for other quantum field theories. The strong force has its own version called quantum chromodynamics. The weak force is handled by electroweak theory, which unifies electromagnetism and the weak interaction. But QED came first and set the standard. And here is something charming. Despite its mind-bending math, QED is deeply intuitive once you get the hang of it. Feynman himself used to say the rules of quantum electrodynamics could be written on the back of a napkin. In his characteristic style, he summed it up like this: particles take all possible paths, each with a probability amplitude. You square the sum to find the actual probability. And that is it. The rest is just accounting. This idea that nature explores all paths is at the heart of the quantum worldview. An electron doesn't just go from point A to point B, it takes every road through every obstacle, around every tree and under every stone, calculating all these possibilities. And QED is how we spy on that process. It is also a testament to how strange quantum physics can be without falling apart. You might think surely a theory this weird must have limits, and you would be right. QED doesn't include gravity and doesn't explain dark matter, but within its domain, it reigns supreme. It is simply the most precisely tested theory in the history of science. Even Feynman, who was famously skeptical of excessive awe, admitted QED was extraordinary, but he also warned us not to get too comfortable. Nature, he liked to say, always has more cards up her sleeve, and while QED might be the best theory we have, it might not be the best theory we can have. Still, for now, it is a masterpiece, a theory that began in tangled math and philosophical frustration and emerged as a clear, precise description of the quantum heartbeat of the universe, light and matter interacting in an eternal whisper described with such grace that even the decimals seem impressed. And in that whisper lies the light of distant stars, the pulse of your smartphone screen, and the soft glow of a bedside lamp, all choreographed by a theory so subtle you barely notice it working, but it is there in every flicker, every reflection, every breath of illumination. Quantum electrodynamics, a silent triumph, a dance written in fields and photons, performed billions of times a second and always without fail, leaving an echo. If classical computers are like carefully trained librarians, efficient, orderly, and great at flipping through books one page at a time, then quantum computers are more like very strange poets who read all the books at once in overlapping whispers and somehow still find the answer. It seems like magic, and in a way it kind of is. But quantum computing is real, and it is built on the same bizarre principles that make up the heart of quantum physics. To understand what makes a quantum computer different, you first need to meet the bit's weirder cousin, the qubit. In a classical computer, everything comes down to bits. A bit is a binary unit of information. It can be 0 or 1, like a switch that is off or on. These bits are the building blocks of everything your computer does, from streaming videos to calculating your taxes, and classical computers are great at manipulating many bits very quickly. But a qubit, short for quantum bit, doesn't just live in a state of 0 or 1. Thanks to the magic of superposition, a qubit can be in a mixture of both states at once. Imagine a spinning coin that is neither heads nor tails until you stop it and observe the result. While it is spinning, it holds the potential for both outcomes. This means a single qubit holds more than one state simultaneously. And as you add more qubits, the power of this superposition grows exponentially. 2 qubits can hold 4 possible combinations, 3 qubits hold 8, 20 qubits hold over 1,000,000. With enough qubits, a quantum computer could, in theory, explore an astronomical number of possibilities in parallel. That is the key idea behind quantum computing, parallelism. While a classical computer tests each path one by one, a quantum computer explores many paths at once, though not in a way that gives you all the answers instantly. The trick is to manipulate the system so that when measured, the correct answer is the most likely to appear. It isn't a brute force guess. It is more like shaping the probability landscape so the right solution rises to the top. But there is another quantum trick up its sleeve: entanglement. When qubits become entangled, the state of one is linked to the state of another, even across distances. This allows complex correlations between qubits that classical bits simply cannot replicate. It is like a dance between particles. If one spins, the other spins too, no matter how far apart they are. This entanglement allows quantum computers to perform operations that would take classical machines enormous amounts of time and energy. For certain problems, like simulating molecules or factoring large numbers, quantum approaches promise massive speedups. But now comes the part where we slow down and take a breath. Quantum computers aren't going to replace your laptop anytime soon. They are specialized tools, not general-purpose devices. For tasks like browsing the web or editing a video, your classical computer remains the champion. In fact, building and operating a quantum computer is hard. Qubits are incredibly delicate. They can be disturbed by tiny vibrations, temperature fluctuations, even stray magnetic fields. Maintaining a qubit's coherence, its ability to stay in superposition and entanglement, requires extreme care. Many systems must be cooled to temperatures near absolute zero, that is colder than deep space. And then there is error correction. In classical computers, if a bit flips unexpectedly, it is pretty easy to spot and fix. In quantum systems, it is much more complicated. You can't just copy the state of a qubit without disturbing it, thanks to the no-cloning theorem. So researchers have had to invent clever schemes, using many physical qubits to protect one logical qubit. It is like wrapping your whispering poet in layers of soundproofing so they can keep reciting without interference. Despite these challenges, progress has been impressive. Companies and research labs have built quantum computers with dozens to hundreds of qubits. Some have demonstrated quantum supremacy, performing tasks that would take a classical computer an impractical amount of time. Others are developing systems known as NISQ devices, short for Noisy Intermediate Scale Quantum, which explore what we can do with imperfect but still useful quantum machines. And there are real-world applications being explored. One promising field is quantum chemistry. Simulating the behavior of molecules at the quantum level is incredibly difficult for classical computers, but quantum machines are naturally suited for it. This could revolutionize materials science, drug discovery, and even battery technology. Another exciting area is optimization, solving problems with many competing variables, like finding the best delivery routes or allocating resources efficiently. Quantum algorithms might be able to find solutions faster and with fewer steps than traditional methods. And then there is cryptography. Some quantum algorithms, like Shor's algorithm, could one day break widely used encryption methods by factoring large numbers incredibly fast. This has sparked a new branch of security known as post-quantum cryptography, where researchers are designing encryption schemes that even quantum computers can't break. Still, we are in the early days. Most quantum computers today are noisy, fragile, and limited in what they can do. The dream of a large-scale, fault-tolerant quantum computer is still years, if not decades, away. but that doesn't make the journey any less fascinating. What is particularly enchanting is how quantum computing takes the strangest parts of quantum mechanics, the parts that once seemed like philosophical puzzles, and turns them into tools. Superposition, once a curiosity, becomes a resource. Entanglement, once ghostly, becomes useful. Even measurement, that act of collapsing possibilities into a single outcome, becomes a step in the calculation. It is almost poetic. The very weirdness that made quantum theory so unsettling is now being harnessed to solve problems once thought impossible. It is like taming a wild wind, not by fighting it, but by sailing with it. Quantum computers invite us to rethink what it means to compute. They challenge the boundaries between certainty and probability, between logic and fuzziness. They remind us that beneath the surface of classical reality lies a much stranger landscape, one where information is smooth and tangled, and answers emerge not from single steps, but from orchestrated patterns of possibility. We might not know exactly where this quantum path will lead, but the journey itself, quiet, intricate, full of potential, is already rewriting our understanding of what machines and minds can do. In the quantum realm, we expect things to be weird. Subatomic particles teleport through barriers, spin in two directions at once, and form entangled pairs that whisper across the cosmos. But there is one place we generally don't expect to see quantum behavior: biology. Biology is messy, warm, and wet. It operates in a noisy world, full of vibrating molecules, random collisions, and fluctuating energy. Quantum effects, on the other hand, are notoriously fragile. They are easily disturbed by heat and chaos. That is why we build quantum computers in freezing labs and isolate particles in high vacuum chambers, and yet somehow life seems to be using quantum tricks of its own. Take the European robin, for example, a small, unassuming bird with a surprising sense of direction. Robins are migratory, flying thousands of miles with incredible precision. But what is guiding them? How do they know which way is north? Scientists long suspected birds had a built-in compass, but the details of how it worked remained elusive. Then came a radical idea: could quantum entanglement be involved? The hypothesis goes like this. Inside a bird's eye, there might be a protein, likely called cryptochrome, that contains a pair of entangled electrons. When light hits the molecule, it excites these electrons, causing them to become quantumly linked. Their entangled spins then interact with the Earth's magnetic field, influencing a chemical reaction in a way that depends on the direction the bird is facing. If that sounds like science fiction, you aren't alone. The idea was met with skepticism. Entanglement is delicate. Could it really survive inside a living cell amidst jostling proteins and bustling water molecules? Surprisingly, early experiments suggest it might. There is growing evidence that birds really do rely on a quantum process to detect magnetic fields. It isn't fully proven yet, but the signs are promising. If true, it means nature has figured out how to preserve quantum information in a biological environment, something human engineers still struggle to perfect. Now let's shift to something green and leafy. Plants, like birds, are masters of a subtle quantum game. Consider photosynthesis, the process by which plants turn sunlight into chemical energy. It seems simple enough. Light hits a chlorophyll molecule, which absorbs the energy and transfers it to a reaction center where it is stored. But how does that energy get there so efficiently? You might think it bounces randomly from molecule to molecule until it hits the right spot. That would be a slow, clumsy method, but measurements suggest something much more elegant is happening. The energy seems to explore multiple paths simultaneously, as if the system is using quantum coherence to find the most efficient route. Imagine dropping a marble into a maze, and instead of rolling down one corridor, it spreads out like a wave, filling out all possible paths, and then settling on the shortest one. That is how some researchers believe photosynthetic complexes behave. The energy doesn't wander aimlessly. It takes the best route thanks to a bit of quantum navigation. This is astounding because these systems are warm, biological, and noisy. Yet, quantum coherence seems to persist long enough, sometimes on the scale of picoseconds, which in the molecular world is a decent amount of time to influence outcomes. If plants are quantum strategists, this raises a tantalizing possibility. Evolution has learned to harness quantum mechanics. There is no reason to think biology can't make use of the same principles we find in physics labs. After all, nature has had billions of years to experiment, and organisms that found clever quantum shortcuts, whether for energy efficiency, navigation, or sensing, might have enjoyed a survival advantage. Speaking of sensing, there is one more biological mystery that might have a quantum answer: smell. We usually imagine smell works by shape. A molecule fits into a receptor in your nose like a key in a lock, and boom, you detect the scent. But this theory has some gaps. Molecules with similar shapes can have very different smells, and some molecules with different shapes can smell exactly the same. An alternative idea is the vibrational theory of olfaction, which suggests our noses don't just detect shape, they detect how molecules vibrate. The proposal is that when a molecule binds to a receptor, electrons in the receptor can tunnel through the molecule, and the probability of tunneling depends on the vibrational frequency of the molecule. If true, it would mean part of your sense of smell involves quantum tunneling, the same trick that allows particles to pass through barriers in nuclear fusion. Your nose might be sniffing in stereo, both structurally and vibrationally, using quantum mechanics to help decode the invisible world of molecules. Again, the idea is controversial, but experiments have shown that people and even fruit flies can sometimes distinguish between molecules that differ only in vibrational frequency. It isn't conclusive, but it is enough to keep scientists intrigued. Quantum biology is still in its infancy. Much of the field is built on bold ideas, tentative experiments, and more questions than answers. But what makes it exciting isn't just the novelty, it is the reminder that the strange rules of quantum physics don't stop at the lab bench. They reach into the feathers of birds, the leaves of trees, and the air you breathe through your nose. It is a humbling thought. The same math that describes the behavior of electrons in a vacuum also underpins the song of a robin and the glow of sunlight on a leaf. Nature doesn't separate its domains. Quantum effects aren't locked away in some microscopic vault. They are everywhere, woven into life itself. And perhaps as we learn to understand these quantum tricks, we will gain not just new technologies, but a deeper appreciation for the ingenuity of evolution. Life, it seems, has been playing with the universe's strangest tools all along. They just never bothered to tell us. At the quantum level, particles do strange things. They blur into superpositions, interfere with themselves, and occupy multiple possibilities at once. It is the playground of probability, not certainty. And yet, when you look around, you don't see a world made of shimmering maybes. You see a coffee mug, a table, a cat that is hopefully alive or dead, but not both. You interact with a world that seems solid, consistent, and wonderfully predictable. Why is that? Why don't you see tables that are both here and there? Why don't whole sandwiches exist in a wave of probability, collapsing only when you open the fridge? The answer lies in a silent but powerful process called decoherence, the mechanism that explains how the quantum world gradually loses its quantumness and becomes the classical world we know. Let's start with a quick mental stretch. Imagine a single electron in a superposition. It isn't in one place, it is in a scatter of possibilities. You can't tell exactly where it is until you measure it, and yet you are just encouraging it to pick a location. Now imagine that electron is left alone in the vacuum of space, completely isolated. It remains in that beautiful, delicate superposition. But back on Earth, things aren't so quiet. There is air, heat, photons from the sun, bouncing molecules, vibrations, fields, and background radiation. The moment your quantum object interacts with any of these things, it starts to lose its quantum coherence. The neat mathematical interference patterns start to blur, that is decoherence. It isn't that the superposition disappears. It is still there in a sense, but the quantum system becomes entangled with the environment, meaning all those particles it touches become part of its quantum description. And when that happens, the system stops behaving like an isolated wave of probabilities and starts behaving like something ordinary, predictable, measurable. You can think of it like this: quantum systems want to be private. But the moment the environment peaks, they lose their privacy, not because someone measured them with fancy equipment, but because nature itself is always watching. Air molecules, photons, vibrations. All these things act like tiny, constant observers. They don't collapse the wave function, but they blur its coherence, making interference impossible. Decoherence is a gentle erosion, not a violent snap. It doesn't require a conscious observer or a big dramatic measurement. It just takes time and contact with the outside world, and it happens incredibly fast. For microscopic objects like electrons or atoms, you can isolate them well enough that quantum behavior persists. But for macroscopic objects, things you can touch, see, or eat, decoherence happens almost instantly. The more massive and complex the system, the faster its quantum weirdness dissolves into classical certainty. In fact, decoherence timescales for large objects can be trillionths of a second or less. That is why you don't walk into a room and find your shoes in a quantum blur. Their interaction with the world has already locked them into a definite state. In this way, decoherence doesn't destroy quantum superpositions, it hides them. The superpositions still exist in principle, but they are now entangled with so many environmental degrees of freedom that you can't access or reverse them. They become effectively classical, even though deep down everything remains quantum. This also helps explain one of the long-standing mysteries of quantum mechanics: how we get from probabilities to outcomes. Decoherence doesn't completely solve this puzzle. It doesn't choose which outcome occurs, but it helps explain why we don't see quantum interference in large systems. Why Schrödinger's cat, if left unobserved, doesn't literally hover between life and death. On your kitchen counter, decoherence creates the illusion of collapse by leaking quantum information into the environment. The result is a sort of statistical consensus. The wave function is still there, but it no longer behaves in a coherent, observable way, and this gives us a bridge between the quantum and classical worlds. Classical physics is still a useful tool. It is how we build bridges, launch rockets, and bake soufflés, but beneath it all the universe hums with quantum rhythms. What decoherence does is gently veil that underlying weirdness, creating the robust world we experience. A helpful way to visualize this is like walking on a frozen lake. Beneath the surface, the water is shifting, fluid, quantum. But the ice is solid and reliable. Decoherence is what freezes the surface. It doesn't eliminate the water underneath, it just keeps it out of reach. And the more connected an object is to its surroundings, the thicker that ice becomes. This also has practical consequences for technology. Quantum computers, for example, have to fight decoherence constantly. Their qubits are delicate, and even a stray vibration or thermal fluctuation can collapse their quantum behavior. That is why they are kept in ultra-cold, isolated environments to extend their coherence as long as possible. Without that, the quantum advantage vanishes. Decoherence also plays a role in interpretation. Some theories suggest there is no need for a separate wave function collapse. Instead, decoherence explains why certain outcomes seem definite. It isn't that the universe chooses an outcome, It is that the alternatives become unobservable due to entanglement with the environment. The tree still falls in the forest, but its echo is muffled by the noise. It is worth noting that decoherence doesn't solve all the mysteries of quantum mechanics. It doesn't answer why a specific measurement produces a specific result, or whether the wave function is real or just a mathematical tool, but it explains why the quantum weirdness fades. The classical certainty of daily life shows us that the world we see isn't separate from the quantum realm. It is shaped by it, filtered through a continuous interaction with everything around us. So the next time you pick up a mug or open a door, you can thank decoherence for the fact that it behaves the way you expect, for taking a universe of maybes and presenting it as a firm handshake. It is a silent phenomenon, no sparks, no arrows, just a slow, graceful loss of possibility, leaving behind the stable patterns we call reality. Imagine setting up an experiment so strange, so delicate, that the very act of deciding when to observe seems to reach back into the past and affect what happened before. It sounds like science fiction or perhaps science confusion, but it is precisely what happens in a series of experiments that toy with the very foundation of cause and effect. They go by names like the delayed choice experiment and the quantum eraser. And if you were hoping quantum physics would finally start making sense, well, this is the point where even time itself starts to shrug. Let's start with a familiar setup. The double-slit experiment. Fire a beam of photons or electrons, or even molecules at a wall with two slits. Behind the wall is a screen to catch what gets through. If you don't observe which slit the particles go through, they create an interference pattern, a series of light and dark bands, as if each particle went through both slits and interfered with itself. But if you put a detector to find out which slit each particle passes through, the interference vanishes. The particles act like tiny bullets instead of waves. Simply knowing the path kills the wave behavior. So far, weird. Now let's get mischievous. In the delayed choice experiment, originally proposed by physicist John Archibald Wheeler, you set up your experiment without measuring the particle's path, but you reserve the right to decide whether to measure it after the particle has already passed the slits. In other words, you delay your decision. Are you going to act like a curious detective and observe the path, or are you going to let the particle remain mysterious and wavy? This is where it gets surreal. The pattern on the screen will match the choice you make, even if that choice happens after the particle supposedly decided how to behave. It is as if the particle somehow knows what your future choice will be and adjusts its past behavior accordingly. It either produces an interference pattern, wave behavior, or not, particle behavior, depending on an event that hasn't even happened yet. It is enough to make a clock melt. The delayed choice experiment suggests the quantum world doesn't commit to a specific reality until forced, not just in space, but in time. The act of observation doesn't just determine the outcome, it can determine the history. And then quantum physicists said, let's make it even weirder. Enter the quantum eraser. In this twist on the double-slit setup, you tag the particles so you can know which path they took, but then you use a clever trick to erase that information after they have been detected. And when you do this, when you erase the which path information, after the fact, the interference pattern comes back. The particles behave like waves again, retroactively, as if they never abandoned the ghost of uncertainty. This raises a deeply unsettling idea. Reality might not be finalized until all possible information is resolved, not just at the moment of detection, but at the moment we decide what to do with the information about that detection. It is like a cosmic version of Schrödinger's cat, but stretched across time. Not only is the cat both alive and dead, but whether it was alive or dead depends on a decision made after you opened the box. So what is going on here? One tempting interpretation is that information, not physical matter, is the true currency of the universe. In the quantum world, outcomes aren't fixed until you ask questions that have answers. Until then, all possibilities remain entangled in a blurry soup of maybe. This doesn't mean time travel is real or that we can change the past. Instead, it suggests our usual picture of time as a one-way street might not apply at the quantum level. Events in the quantum realm aren't chained by neat links of cause and effect. They are part of a strange holistic web where outcomes only emerge when the entire system is considered. Still, there are limits. Although these experiments are astounding, they don't allow communication with the past. You can't send messages backward in time or change what has already happened. The results always play by the rules of causality at the macroscopic level, but they suggest that beneath the surface those rules are a bit more flexible. Some physicists describe this in terms of entanglement and correlation, not causation. The particle doesn't know what you will do in the future. It is that all the pieces of the experiment are connected in such a way that your final setup defines which patterns are visible. Others lean toward a block universe interpretation, where all moments in time exist simultaneously like frames on a film reel. In this view, your choice isn't something that travels backward. It was always part of the grand timeless quantum story, and still others just shrug and say, "Shut up and calculate." The important thing is this: the universe has no obligation to conform to our common sense ideas about time, cause, or measurement. Our classical intuitions are built for macroscopic objects, rocks, coffee mugs, and cats, but down in the quantum mist, the rules are subtler, less linear, less local, and much, much stranger. The delayed choice and quantum eraser experiments don't break physics. They reveal the richness beneath it. They show that the quantum world isn't just a smaller version of our everyday world. It is something fundamentally different, playing by a logic of its own. So, if time ever seems to be playing tricks on you, just remember, at the quantum level, it probably is. If you could zoom in far enough into the heart of the universe, past the galaxies, past the molecules, past the atoms themselves, you would eventually reach a world where certainty quietly slips through your fingers. A world where outcomes aren't determined but described in terms of probabilities, where particles don't have positions until you look and yet are merely the result of a cosmic roll of the dice. Welcome to the quantum universe, a place that isn't just small, it is uncertain. At its core, quantum physics suggests that randomness might not just exist, but might actually rule. This idea doesn't please everyone. In fact, it made Albert Einstein famously uncomfortable. He once declared, "God does not play dice with the universe," a phrase that has been quoted for nearly a century in every philosophical coffee shop conversation involving physics and fate. But let's unpack what this randomness actually means and what it doesn't. In classical physics, everything behaves like a well-oiled machine. If you know the position and velocity of every particle in a system, you can predict the future with absolute precision. It is a neat deterministic framework, like lining up dominoes and knowing exactly how they will fall. Quantum mechanics breaks that chain. It replaces precise predictions with wave functions, mathematical objects that describe all the possible outcomes of a particle's behavior. And when you make a measurement, the wave function collapses into one of those possible outcomes. But which one do you get? It isn't determined in advance. It is genuinely random. This isn't code for "we don't know yet." It isn't the result of human error or missing information. It is baked into the very structure of reality. The best you can do is calculate the probability of each outcome and accept whatever shows up. Now, some interpretations of quantum mechanics, like the many worlds view, avoid this randomness by suggesting every possible outcome happens just in a separate branching universe. So when you measure a particle and it has spin up, the other version of you in another universe sees spin down. No randomness, just infinite outcomes. But even if that is true, you still can't predict which version you will find yourself in. From your perspective, the experience is just as unpredictable. And this raises some deeply philosophical questions. If randomness exists at the base of reality, what does that mean for cause and effect, for free will, for the very laws of nature? It can seem unsettling at first, the idea that the universe isn't operating on some grand script, but improvising along the way, that there is a fundamental looseness in the fabric of reality. And yet, randomness isn't the same as chaos. In fact, quantum mechanics is astonishingly precise in its predictions. It doesn't say just anything can happen. It says, here is a list of what can happen and the odds of each. When physicists have tested quantum predictions, like those of quantum electrodynamics, they have found agreement with experiments to 12 decimal places. It is like predicting the height of Mount Everest to the precision of a human hair. So even though quantum outcomes are random, the structure of that randomness is deeply ordered. It is a bit like rolling 6 dice and finding they always add up to a predictable average, even though each die falls randomly. The outcomes are probabilistic, but the behavior of a large number of particles becomes so reliable that it gives rise to the laws of classical physics. That is why your coffee mug doesn't suddenly tunnel through the table, even though individual particles can. In this sense, randomness isn't a bug, it is a feature. It adds flexibility to the universe, allows for novelty, and might even be essential for life, creativity, and consciousness. Think of mutation, of evolution. If every biological event were strictly determined, there would be no variation, no branching paths. But add a little randomness, a gene shift here, a transmutation there, and suddenly the universe has options. Some of those options lead to leaves, others to leopards, others to philosophers. In the quantum realm, randomness is the engine of variety. It gives rise to complexity from simplicity, and it does so without breaking the rules, because the rules of quantum mechanics are statistical, not prescriptive. Some scientists and philosophers find comfort in this unpredictability. After all, a deterministic universe can feel like a clockwork prison, where every thought, action, and feeling is just the echo of particles obeying rigid laws. But a probabilistic universe, that is one where the unexpected can happen, where outcomes aren't written in stone but drawn from a deck. Of course, randomness also comes with mystery. When we observe a particle in one state instead of another, why that one? Quantum mechanics offers no reason, it just gives you the odds. It is like flipping a coin and getting heads. There is no deeper explanation for that outcome, just that it had a 50% chance. And that carries philosophical weight. It suggests the universe isn't fully knowable in the classical sense. There is a ceiling to certainty, a boundary beyond which questions don't have definite answers, just bands of possibility. And yet, we can still thrive in that uncertainty, build technologies from it, find meaning in it. Quantum randomness also ensures no two things are truly identical. Even particles prepared in the exact same way will sometimes yield different results. That tiny irregularity, that whisper of unpredictability, is what keeps the universe alive and interesting. So maybe the universe does play dice, yes. Not recklessly, but with an elegance so refined it creates galaxies, atoms, thoughts, and time itself. And while we might never fully tame that randomness, we can come to appreciate it, not as a flaw in the cosmic machinery, but as the soft hum of possibility woven into the fabric of everything. If quantum physics were merely a set of equations, no matter how strange, no matter how elegant, it could still be considered one of humanity's greatest intellectual achievements. But what makes it truly special is that it doesn't just describe particles and probabilities. It invites us to reflect on something deeper, what it means to know and what it means to be. Because in peeling back the layers of the universe, quantum physics doesn't simply reveal new answers, it reshapes the very questions. We have a tendency to think of reality as something solid, fixed out there, something that exists whether we are here to look at it or not. But the quantum world softly, persistently disagrees. It suggests that at the smallest scales, reality isn't fixed. It is a set of possibilities, like dreams waiting for an observer to nudge them into shape. When a particle exists in a superposition, it isn't just undecided. It is all its possible states at once, a smear of probability, not a single point. And when we measure it, it settles into an outcome, as if the universe softly exhales and chooses a story. This raises a quiet, unsettling thought. If observation plays such a crucial role in shaping outcomes, are we really as separate from the universe as we believed? Or are we, the observers, and everything else part of the grand, entangled dance? To physicists, these are technical questions. To the rest of us, they feel almost spiritual. But quantum physics isn't here to offer easy answers. It isn't a shortcut to enlightenment or a metaphor factory for self-help books, and yet it leaves us with something precious: humility. It reminds us that our everyday intuitions about space, time, matter, and cause aren't the final word on how things work. That the familiar world we navigate every day is just one version of reality, filtered by evolution, shaped by our senses, and stitched together by habit. In this way, quantum mechanics becomes more than physics. It becomes a mirror, showing us the edges of our knowledge, the limits of our comprehension, and the breathtaking strangeness of the universe we call home. Think of Schrödinger's cat, not as a literal feline trapped in a paradox, but as a metaphor for how we live in uncertainty, for how we constantly balance conflicting possibilities, half-knowns, and near certainties. Whether waiting for a medical test result, applying for a job, or just wondering if it will rain tomorrow, we exist quite often in a quantum state of our own: hope and fear, expectation and doubt, possibilities softly overlapping until time or choice collapses the wave. And perhaps that is the secret beauty of quantum mechanics. It isn't telling us the world is unknowable or meaningless. It is just telling us it isn't obliged to be obvious. There is a softness in this realization, a quiet freedom. If certainty isn't guaranteed, then limitation isn't either. If the world isn't fixed until observed, then possibility is always alive, flickering just out of sight. Even the word quantum has a sort of poetry. It comes from the Latin quantus, meaning how much. How much light, how much energy, how much this or that particle is allowed to be or do. But more than that, it is a word that points to boundaries, discrete and indivisible packets, the smallest unit of change allowed. And perhaps there is something meaningful in that too, that even in the vast, turbulent mass of the cosmos, there are limits, minimum steps, quiet thresholds that must be crossed. Not everything is continuous. Some things change in leaps. When you dream, you don't do it one atom at a time. You leap into worlds that don't exist until they do. You witness impossible things until they seem natural. And when you wake, you might not remember all the rules, but you bring back the feeling of possibility. Quantum physics feels like that, like waking from a dream and realizing the world is stranger, wilder, and more wonderful than you ever imagined. Of course, that can be a bit unsettling. We like cause and effect. We like knowing. Certainty has its comforts, but perhaps it is also a bit overrated. Maybe it is okay to live with questions that don't have answers yet, to wander in a forest of probabilities without demanding to know which tree is real. Perhaps that is where wonder lives, in the spaces between what we can grasp and what we can only glimpse. The physicist Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." He meant that as much as a joke as a truth. Even those who work with the math every day, who build machines and models from its predictions, will admit that quantum physics isn't something you understand in the usual way. It is something you accept like a poem or a dream. It works, it is precise, it is testable, and yet it refuses to be pinned down by common logic. And perhaps, just perhaps, that makes it more honest, because the universe was never obliged to be simple, it just had to be. So as we float now through the silent ripples of quantum thought, perhaps the most important lesson isn't about particles or probabilities, but about perspective. Seeing uncertainty not as a flaw, but as a feature. Gently letting go of the need to know everything and resting in the strange, beautiful truth that we are part of a cosmos that is still unfolding, still choosing, still shimmering with possibility. A place where even the emptiest vacuum isn't truly empty, where time can flex, where light forgets how to behave, and where, in the end, reality dreams too. Thank you for listening. Whether you are still wide awake, drifting softly, or already halfway into a dream, we have traveled a long way tonight. Through slits in cardboard, thought experiments with cats, rippling fields, and mysterious erasers of time. We have met particles that act like waves, waves that act like particles, and forces that play by rules written in a language we are only just learning to translate. And somewhere along this journey, we began to see not just the weirdness of the quantum world, but its quiet beauty. At first glance, it might all seem too strange to be real. A universe where something isn't truly something until observed, where cause and effect get blurry at the edges, where a particle can be here and also somewhere else. But what quantum physics gently reminds us over and over is that the world we know, the one we can touch, taste, and measure, is just the surface. Beneath it lies a softer world. Stranger, yes, but also more flexible, more open to surprise. A world built not on certainty, but on shimmering possibility. We are part of that world, not separate from it. Not mere observers peeking in from the outside, we are made of those same quantum fields, the atoms at your fingertips, the light reflecting in your eyes, the oxygen in your lungs, all obey the same uncertain laws. You aren't just in the universe, you are of the universe. And doesn't that feel a little poetic? At the beginning, I asked what part of the world you are listening from. Maybe you are curled up in bed listening under a heavy blanket. Maybe you are staring at the ceiling, thoughts flickering like stars. Maybe you are far from home or just far from sleep. Wherever you are, I hope you found something in this journey, something soft or strange or simply still. And remember, when we look into the heart of matter and ask what is real, quantum physics doesn't offer a final answer. It offers a mirror, a shifting mirror, a reminder that knowing something deeply doesn't always mean understanding it completely, that questions can be as beautiful as answers, that mystery isn't a flaw but a feature. It can be tempting to wish for more clarity, to want the universe to lay out its rules plainly and play fair, but perhaps in this tangled uncertainty, there is a different kind of comfort, a gentle truth that says, you don't need all the answers to feel at home here, because even if particles are uncertain, the moment you are in is real. The breath you just took, the thought that just passed, the weight of your body sinking softly into the quiet. That is quantum too, and it is enough. So, thank you for giving your time, your ears, and your quiet curiosity to this little exploration, for trusting the weirdness, for sitting with the not knowing, and if you have already fallen asleep, wonderful. The quantum world will still be here when you wake. From the Deep Field channel, good night.